Good morning, everyone. So, can you hear me at the back? First of all, welcome to the ICTP. Welcome back. There's many people I can see visiting again, but it's nice to see some new faces around. And welcome to the conference. I'm just going to spend a few minutes talking about the ICTP, the Institute itself, so that I'm hoping during the course of the week, those of you that are not so familiar with it will familiarize yourself with some of the things we do, because we're not just a research institute, as I will show you. So we're actually in our 60th anniversary year, and this conference is one of our 60th anniversary sort of flagship events. We don't normally host such big conferences here at the ICTP, only for sort of special reasons. It was founded in 1964 by Abdus Salam, who you know got the Nobel Prize together with Weinberg and Glashow for the discovery of the invention, let's say, of the standard model of particle physics. And the unique thing about it is that we combine high-level research together with a mission for capacity development and the fostering of science in the global south. And the Institute is governed by the Italian government, UNESCO, and the International Atomic Energy Agency, although most of the funding comes from Italy. Broadly speaking, what we do here can be streamed into three categories: research, education, and outreach. So I'll tell you just briefly a little bit about each of those. These are the main research sections at the ICTP. The conference that we're at this week is jointly organized by High Energy Physics and Mathematics, naturally, because we have people studying string theory in the high energy group, and there's an interface with some of our mathematicians. But there's a condensed matter group. We study different aspects of the Earth, the physics of the Earth. The quantitative life sciences group and an innovation group. In terms of research, the ICTP has been involved in several, for example, Nobel Prize winning aspects of research. So now move on to education. These are the sort of main educational programs that we have. We have joint PhD. Since we're not a university about degrees, but we have strong collaborations with neighboring institutions. So CISA being one of them, and the University of Trieste being another. There's also collaborations with University of Udine. These are the various programs that you could learn about whilst you're here. Our main, let's say, educational program is what's called the Postgraduate diploma. That has been running since 1991 and is only for students from developing countries that obviously get selected and they are fully funded, but it's only for students from developing countries in which there's no comparable program. And we have diploma programs in high energy physics, mathematics, condensed matter, and earth systems physics. And this is a crucial program which enables students from many developing countries to go on towards PhD programs. have a significant number of training activities going on of various kinds. So there's around 60 to 70 happening every year. Here's some numbers and some distributional data. This is probably a couple of years old now, but it hasn't changed much. But one key thing is that ICTP supports scientists throughout their entire career, starting from the diploma program and then going on sort of diploma and master's programs, PhD. After scientists, after scientists return to their home country or to another country, we support them throughout their careers, through our associates program and related programs. So associates of the ICTP are scientists working in a developing country and this associates program enables them to come every year for 6 years or so, and scientific research, scientific outreach. We have the Office of External Activities, which supports different kinds of activities and networks around the world. In the last 10 or so years, the ICTP has developed partner institutes. So some of you will know the one in Brazil, the South American Institute for Fundamental Research, or the one in Rwanda, the East African Institute for Fundamental Research. Those are going very well. There's a program called Physics Without Frontiers that I helped found and I run together with a few colleagues. And there's a scientific dissemination unit. Since I run the Physics Without Frontiers program, just to give you an idea of some of the things that we do. Last year we organized 18 projects, actually 30 or so events in many different countries, which I don't know if you can actually read any of this, but you can see. Well, there's the LATAM project. Daniel, who runs that, is here. So we had projects in Nepal, Cameroon, Rwanda, Bhutan, Ecuador, Kurdistan, Afghanistan, Colombia, Ghana, Lesotho, Zimbabwe, another project in Ecuador, and a project in Kenya. So these are actually mostly volunteer-led programs, so if anyone's interested in getting involved, please let me know during the course of the week. I'll skip that. Also, in terms of kind of more regular outreach, we have, distinguished lecture programs, the Salam lectures taking place every year. This is just to show that our support does lead to some real success stories. So some of you will know Freddie Cacciazzo. So he was a diploma student here in the 90s. And similarly, Narayan here was also. Zora has been an ICTP associate for many years, and it's another success story. So I'll finish with a couple of testimonials and then mention a couple of things about the conference. You can read here a testimonial from Stephen. Another one from David Gross. And And the conference, which we're here for. So, as you will have seen, we've got a very nice program of talks and poster sessions as well. I want to mention that the conference, apart from the ICTP and apart from those of you that have paid registration fees, is sponsored also by CISA, our neighbouring institute, the INFN, which is the National Institute for Nuclear Physics, and IGAP, which is the Institute for Geometry and Physics, which is also here and is a joint venture between ICTP and CISA. And then I want to mention, in particular, the co-organisers of the meeting. So, Claudio Arezzo, who's in the maths section, Francesco Benini from CISA, who's here, Agnese Bisi, my colleague in the high energy group here at the ICTP, who's there, Giulio Bonelli from CISA, probably here somewhere, Lothar Gerscher from the maths section, Pavel Putrov, who's jointly maths and high energy. I saw him, he's around. Alessandro Tanzini, who's also, there he is. And Don Zagier, who's a visitor in the maths section, or visiting professor in the maths section. Anything else that I need to mention about the conference or organisation? Well, at the end of the week, we will mention all of the staff that have been involved in the organisation of this meeting, which is a significant number of staff. We have something like 240 registered participants here, and everyone has to be processed in some way administratively, so that our administrative colleagues have been helping with that. But we will thank them at the end. So with that out of the way, please do take time to familiarise yourself a bit with the ICTP whilst you're here. And there's a lot of information on the website. You can talk to people. I would much rather people come and learn something about the Institute as well as participate in the conference, rather than just come to a conference and then go home without learning anything about the Institute. So with that out of the way, I'm going to hand it over. Do you want to say anything, Francesco? No. So with that out of the way, I'm going to hand it over. We can actually begin the conference, and I'm going to hand it over to Ron Donaghy, who's going to chair the first session.
My slide. And you need to show me just how to move around.
Yes. Okay, so you can go forward and backward, and for the electronic.
Which one's forward and backward?
Oh.
Forward and
Forward and
backward.
backward.
Okay.
With this one.
Is the pointer. Oh, great.
Yes.
Excellent. Cool. Very good. Nice up.
You have to unmute the microphone.
No, it's off. What? So I don't know.
Oh, yeah, it's on. Great. Can you hear me? Great. They could hear me, I think.
Anyway, great to start this conference. Welcome to sunny Trieste. It's great to start with Mina Ganagic, who's going to talk about homological link invariance in an A-brain category.
All right, well, it's great to be back to ICTP. The first time I was here, I was a graduate student. So ICTP certainly has been here throughout my career. And it's great to see it going so strong for all these years. All right, so this talk will be mainly about two recent papers with Elise and Miroslav and Ivan, Ishwan, Vivek, Shende, who's here, and Peng Zhou. And it's based on my earlier work. Well, since this is a review paper from the ICM 2022. All right. So the link categorification problem was introduced by Kovanov in 98. Kovanov's link homologies are a collection of bigraded vector spaces, each of which is a link invariant. His link homology theory is a categorification of the Jones polynomial, which arises as its graded Euler characteristic, a signed count of dimensions. Kovanov's construction is part of the categorification program pioneered by Igor Frankel and Crane. A model for categorification is you get by taking a Riemannian manifold whose Euler characteristic is categorified by cohomology groups of the de Rham complex. From physics perspective, de Rham cohomologies originate from supersymmetric quantum mechanics with our Riemannian manifold M as a target space as the space of exact supersymmetric ground states of a given Fermi number. The complex whose cohomology one takes, and the complex which you need to obtain the cohomologies, is the space of perturbative supersymmetric ground states, equipped with a differential that you get by counting instantons. So Kovanov similarly produces link homology groups. Link homology groups by starting with a complex of vector spaces graded by Fermi number and one additional grading, and taking cohomology of the differential. The Jones polynomial is a special case of a Chern-Simons link invariant, or also known as the quantum group link invariant, where you take the Lie algebra to be SU2, and you take links colored by its fundamental representation. Now, Kovanov's construction of these link homologies that categorify the Jones polynomial is completely explicit. However, it leaves as a mystery the physical or geometric origin of his homology groups, because the construction itself is completely algebraic. It also leaves as a mystery what to replace it if you want to get invariance for general Lie algebra. Now, in 2013, Ben Webster provided an algebraic framework for categorification that works for arbitrary ordinary Lie algebras. However, unlike Kovanov's construction, Webster's is purely formal. There's no computation that ever came out of it. The link categorification problem is to find a general framework for construction of link homology groups, categorifying Chern-Simons link invariants, that will work uniformly for all Lie algebras, and that will tell you what these link homology groups are and why they exist, why such a strange question has a good answer. Of course, in the case of the Euler characteristic of a Riemannian manifold, we know why it has a good answer, but why does this one have a good answer? Of course, string theory told us that it should, but anyway. So now, the first known polynomial link invariant is actually much older than the Jones polynomial. It was discovered by Alexander in 1923. Now, the Alexander polynomial is also a quantum group link invariant, However, it's a link invariant not for an ordinary Lie algebra G, but for a Lie superalgebra, GL1/1. And the Alexander polynomial also has a known categorification, however, one that has a very different flavor than Kovanov's. The categorification of the Alexander polynomial is based on Floer theory, which is essentially an A model, which generalizes supersymmetric quantum mechanics to one dimension up, hence the A model. And as such, it automatically comes from both geometry and physics. It's based on target spaces that are products of Heegard surfaces, symmetric products of Heegard surfaces. So this theory is known as Heegard-Floer theory. It was discovered by Orzhvat and Szabo in 2003. So the solution to the link categorification problem, as it turns out, is based on a theory that generalizes Heegard-Floer theory from GL1/1 to all other Lie algebras and Lie superalgebras. It also turns out that many special features exist in this family of theories, which translate to the fact that problems whose solutions you can typically only find formally now exist actually. So we'll find an explicit description of this theory, means of proving that it actually gives you homological link invariants, and an algorithm for computing them. So the theory originates directly from string theory, as I mentioned, as predicted in the works of Oguri and Waffa and Gukov, Schwartz and Waffa, Witten, and also Gayot and Witten. Now, from a mathematical standpoint, this theory is really an application of homological mirror symmetry, which played a key role in formulating and oops, I have to be careful here. How do I get it back to the full screen? Great, okay. Yeah, so it's an application of homological mirror symmetry, which played a key role in discovering the theory, formulating it, and solving it. In fact, a key role for believing that it should actually exist. However, once you've solved the theory, homological mirror symmetry is no longer necessary to formulate the answer. So hence, what I'll describe today is just the answer. So we'll, in fact, get invariants of links in R2 times S1. From them, you get invariants of links in R3 as a special case by simply not considering links that wrap around the S1. So we'll describe the link in R2 times S1 by splitting our R3 manifold into two on a Riemann surface, which is an infinite cylinder, R times S1, and where you choose so that it intersects the links transversely, which you can always arrange. So such a splitting maps the link into a pair of matchings on the Riemann surface, which now has punctures where the two matchings meet. One matching coming from the top and the other one from the bottom. So each matching gives you a collection of non-intersecting curves on the Riemann surface, which end on the punctures. So now pick a Lie superalgebra. So if G is in fact an ordinary Lie algebra, its root system is encoded as usual in the Dynkin diagram, all of whose roots you should consider as bosonic. If you get a Lie superalgebra, then some roots are also fermionic. So we'll color the strands of the link by representations of the Lie algebra, which we take to be minuscule. Now, this minuscule condition is technical, and it's possible that one may be able to relax it, but at the moment, that's what it is. So having chosen the representations that color the strands, and the punctures get colored by pairs of a representation and its conjugate. So to categorify Chern-Simons link invariants, we'll associate to this Riemann surface with punctures a category that depends on the Lie algebra and representations that color the punctures. The category will be a category of D-branes preserving A-type supersymmetry on a Calabi-Yau manifold that's associated with this data. So the category has objects which are A-branes themselves, and it's morphisms that come from open strings that stretch between branes and which you can compose. Our category will have a cohomological Z grading, so a Fermi number, and an additional grading that corresponds to Q of the Jones polynomial, and actually further gradings associated to holonomies of Trasima's gauge field around the S1. So the target space will be based on a product of symmetric products, one for each node of the Dinkin diagram, on the punctured Riemann surface. So you should think of it as just a collection of points on this punctured Riemann surface that are colored by simple positive roots, but otherwise identical. And further, over every bosonic point in Y in our symmetric product, there's a C star fiber, okay, in the full target space. So the A-branes on Y are supported on either products of one-dimensional curves on the Riemann surface, colored by simple roots, or on generalized intervals. So you can describe them explicitly. And further, to fully specify the brane, you also have to pick a brane in the fiber for every bosonic point. So the target is equipped with a holomorphic form and a superpotential. So the category of A-branes you get is a variant of a Fukaya-Seidel category whose objects are graded Lagrangians on the target. The grading, which turns the Lagrangian into an A-brane, an actual object of the category, is a choice of a lift of the phase of omega times e to the minus w to a single-valued function on the Lagrangian. Now, the cohomological grading is a choice of a lift of phase of omega itself. Okay? So, for example, if you change the orientation, it shifts the grading by 1. Now, our category is actually a category of equivariant A-branes because the superpotential is multi-valued. And this introduces additional equivariant gradings coming from a choice of its lift to a single-valued function L. So now, this pair of red and blue matchings will associate a pair of A-branes by replacing the red matchings by sort of these simple interval type branes, and by replacing the blue matchings, so these are intervals in which some collection of color points is moving, and replacing the blue matchings by this, let's call them figure 8 type branes. Generally, they're branes that sort of look like this. They're products of one-dimensional, of closed curves. So the graded space of morphisms, the space of open strings between in the A model between the two branes will turn out to be the link invariant. So the spaces of morphisms between a pair of A-branes are defined by Floer theory, which is modeled after Morse theory, just one dimension up. So the role of the Morse complex is taken by a Floer complex, which is a vector space that's spanned by intersection points of the two Lagrangians. And the Floer differential is that turns your vector space spanned by intersection points into a complex is generated by instantons. So in Floer theory, the action of the differential on one intersection point that takes it to another is obtained by counting holomorphic maps from a strip to your target, interpolating from one point to another of cohomological degree 1 and equivariant degree 0. So the cohomology of the resulting complex is the space of morphisms between the branes. The Euler characteristic you get for free. The Euler characteristic is the equivariant intersection number, which is simply count of intersection points keeping track of gradings. Now, the fact that Euler characteristic is the quantum link invariant is guaranteed to hold here by construction. Namely, this follows from Picard-Lefsch's theory and the fact that the equivariant central charge function, which is generalization of the usual central charge functions for A-branes by e to the minus w is a close cousin of the conformal block of the affine Lie algebra associated to G. And the conformal blocks have the analogous integral formulation as period integrals. This was discovered by Fagin and Edward Frankel and developed by Sheckman and Barchenko. So the actual conformal blocks differ from our equivariant central charge by some insertions that don't affect monodromies and the statements about the Euler characteristic of intersections of Lagrangians. So in what follows, I'll describe this category of A-branes and how to solve the theory exactly. So we'll learn how to compute this homology theory for any link and how to prove that resulting vector spaces are invariant to links. Now, rather than computing the action of the differential by counting homomorphic curves, for which there is no general algorithm, there's no general algorithm in the open string, unlike in the closed string. We'll rather explain how to sum instantons up. So we'll avoid counting disk instantons. So you essentially solve all disk counting problems at once by making homological mirror symmetry that relates the category of A-branes to the category of B-branes manifest. Now, the fact that homological mirror symmetry sums up curve counts, that's its basic property. So the very simplest example of homological mirror symmetry is if you take your mirror pair to be a pair of infinite cylinders. So their torus fibers are simply circles, and the base is just a real line. Now, the categories of branes on the two sides are each generated by a single brane. Now, these branes look different, but their algebra of open strings is the same. It's simply the algebra of functions on a complex cylinder. To see this on the A side, you need to deal with the fact that your target space is non-compact. And mathematicians studying mirror symmetry for the last 20 years have discovered how to do that. And essentially, it's a prediction of the work of Hori and Waffa. But anyway, so what you want to do is you want to tilt one of the branes relative to the other, and then all the intersection points of the branes become transversal. Whoops, I did it again. You need to teach me how to do this, and I need to learn fast. I have to now pay close attention to what you did. Rather, I should not do it again. All right. So anyway, so once you formulate the A model properly, then it's manifest that algebras of open strings on the two sides are the same and simply equal to the algebra of functions on a complex cylinder. And the fact that algebras of open strings are the same turns out to mean that entire categories of branes are the same, both being equivalent to the derived category of modules of an algebra, the open string algebra. So objects of that derived category are complexes of modules of the algebra. And these complexes, what they do is they describe your geometric brane in terms of the generators. Okay. Because the generators are the same, once you have a description on one side of a brane as a complex of the generators on one side, you can just carry it. And the algebra of open strings is the same. You can just carry it to the other side. So the two categories become literally the same via this middle one. So it turns out that our theories will generalize this very simplest example, which is what eventually will make them solvable. So from perspective of why, the generating set of branes are all products of real line Lagrangians colored by simple roots. If your Lie algebra is anything but a GL1/1, or if your root system contains any bosonic roots, then the branes get equipped with an extra structure of a local system, which comes from describing whatever brane is in the fiber. The brane that's in the fiber is simply, well, the fibers are just a copy of C star over every bosonic point, and then in that C star fiber, you just take another real line Lagrangian. Okay, so everything interesting happens in the base. So the open string algebra turns out to be, so the generator here, you'll actually get many branes for all sort of inequivalent ways of distributing your real line Lagrangians in the base. And the actual generator is just a direct sum of those. Okay? So the algebra of open strings between them turns out to be computable exactly. So as a vector space is generated by the intersection points of branes defined by the Rapp-Foucault category. That's the algebra being generated by intersection points of branes is analogous to our model example. You just need to interpret it as intersections in product of symmetric products. Now, these intersection points of Rapp branes, what they really represent is open strings that stretch between pairs of unperturbed branes. So this intersection point maps to this open string in a symmetric product. So these algebra elements are naturally encoded in configurations of blue strings, as many as the dimension of your symmetric products, on a cylinder of unit height whose vertical direction parameterizes direction along the string, and whose circle direction represents the circle in the Riemann surface. So the blue string encode the open string as a path from the starting brane to the final brane. And the punctures on the Riemann surface get represented by these other kinds of strings that are frozen in time, the time along the world sheet. So the open string algebra for the fibers turns out to be very boring. It's just a polynomial algebra due to the nature of the fiber-wise potential. So basically, each fiber alone is mirror to a copy of C with C star action on it. Anyway, so multiplying an intersection point in the base by an element of this polynomial algebra can be represented by post-composing these blue strings by a corresponding number of dots. That encodes the entire information about the intersections in the whole space. So the algebra relations come from Floer product, which translates here into stacking cylinders and rescaling. Now, to compute the algebra structure, we'll start not with y, but with y0 that's y with some divisor deleted. The divisor we'll delete has as its main component the diagonals, where any 2 points of the same color come together on the Riemann surface, along with some additional ones. You'll basically delete everything interesting, okay? All interesting loci. But the most important one is the diagonals. So having done so, we have the equivalence of the category of branes associated with y0 and an algebra, which is the algebra of open strings of the same brane, just with a different target, the target with the divisor deleted. These two categories, they have the same objects, and the generators of all the Floer complexes are the same, since all of them are based on branes that avoid these diagonals. So you haven't lost anything as far as the objects themselves are concerned. And the spaces of morphisms between them. However, the algebra structure will change. So this theory with this divisor deleted turns out to be very simple. Because since you've deleted the diagonal in the symmetric product, it means that the only maps that contribute to the product are one-dimensional maps to the Riemann surface times the fibers, which are easy to count. So these, in general, it is not possible to count maps, but you land in a place where the only maps that contribute are the ones that are algorithmically easy to count. And you learn how to do it in your first course on minor symmetry. The relations, the algebra relations on Y0 turn out to say that all string diagrams must have no excess intersection, or else the algebra product vanishes. So as a result, the algebra you get is an associative algebra that's graded in general by cohomological and equivariant degrees, which is easy to compute explicitly. I just told you the answer. Okay. Now, the theory you actually want is a deformation of the theory in Y0 by putting the diagonal on this deleted divisor back in. And so that theory is a deformation of the original one, of the theory in Y0, where the deformation parameter is the instanton counting parameter. It's the guy that keeps track of the intersection numbers with the divisor deleted. Now, so as vector spaces, the algebra, the simple to compute algebra and the one you want are the same, only the algebra structure deforms. So it turns out that understanding the GL11 and the SU2 theories turns out to suffice to solve the case of general G. So if you think of a Dinkin diagram of a general Lie algebra as having some number of bosonic and fermionic points, every bosonic node is the SU2 node, every fermionic node is a GL11 node, every Lie algebra is composed of those. It turns out once you know how to solve the theory for these building blocks, you're done. And moreover, we're in a fortunate situation where you only need to count 2 single non-trivial disks. One for GL11, which is actually has been done by Haggard-Floyd people long ago, and one highly non-trivial disk for SU2. So in the GL11 case, putting the diagonal divisor back in, the algebra gains a non-trivial differential, which is a cohomological degree 1 operator that removes the crossing. For SU2, now for all ordinary Lie algebras, it turns out that your algebras are just ordinary associative algebras, so there can never be any differential. So instead what happens is that the relations deform, okay, in one place. And computing this correction is the very hard part that we've done in this joint work with Schende, Zhou, and others. So for any Lie algebra, the same strategy works of working in a complement of this diagonal divisor and then filling back in solves the theory. And in fact, you don't need to do any additional work. So for GL11, the endomorphism algebra of these generators turns out to be the algebra that Lipschitz, Oswald, and Thurston constructed in the context of studying Haggard-Floyd theory. This part is not a surprise because the theory is a generalization of theirs. Now, a theorem with this joint work with Schende is the following, that if you take G to be an ordinary Lie algebra, so just bosonic Lie algebra, then the endomorphism algebra coincides with the algebra that was discovered by Kovanov and Lauda, by Roquier, and then later generalized by Webster. These algebras are known as the KLRW algebras. They were discovered for the purpose of categorifying quantum group invariance. And moreover, the fact that for G, which is an ordinary Lie algebra, the algebra coincides with this cylindrical KLRW algebra implies that if you specialize to links in R3, which is what Webster had considered in 2013, the invariance that this gives you will be his invariance, because they're based on exactly the category of modules of exactly the same algebra. Now, his invariants are defined only formally. You can't compute anything, but you know they're going to be the same. For Lie algebras other than GLN/1, the resulting algebra turns out to be new. So now we'd like to apply this to the problem of computing our spaces of morphisms between these cap and cap branes, the former, so one half of which we take to be the simple interval type branes, and the other ones are these braided figure 8 type branes. So the fact that the T-branes generate the category means that any brane in a category can be described as a complex, which is a direct sum of the generators with some differential. So this differential is a degree 1 operator that squares to zero in an appropriate sense. What it is an open string tachyon that gives you a prescription for how to glue the brane of interest out of the generators. So one further simple, I told you that this theory has many properties that help make it solvable. So one of the key things is that half of the branes, these cap branes, the interval type branes, are dual to the generators in the sense that the only non-zero morphisms from the generating brane to these cap branes are, they have sort of a perfect pairing. They're, if you want, they're dual to each other. So that means the following, that if you know the complex that resolves these, the braided cap branes, the complicated branes that look like figure 8s that you have, and the braiding, by simply taking the Hom with, studying the Homs with the I-branes, what you get is a complex of vector spaces. So from this complex, you get for free, with no additional work, a complex of vector spaces whose cohomology we're after. So the only work you need to do is to figure out how to describe this brane of interest in terms of the generators, as a complex of the generators. So this identification of the space of morphisms in the full category of A-branes with the cohomology of this complex that you get from the resolution of the brane in terms of the generators, as its case cohomology, is a tautological consequence of the equivalence of two descriptions. One as some embedded or immersed Lagrangian, and the other one as a direct sum of these straight line branes with some maps between them. Okay? And existence of such things is the key property of the category of branes. If you want, it's the existence of such things, a key property that makes the derived category the derived category. So moreover, to actually do any calculation in derived category, even derived category of B-type branes, you need to know how to find these resolutions. If you cannot find the resolution in terms of the generators, you cannot do a general computation. You can do some computation for some specific things, but the general one you can't. So this problem is there on the B side. So at this point, the B side and the A side are the same footing. So to find this resolution is in general a very difficult problem that people cannot solve. Because you have two separate problems. Well, supposing you know the generators and you can compute then the morphism algebra of the generators, then the two separate problems you need to solve is A, find which brane, find the image of the, which module of your algebra the brane maps to by this functor. It's called the Yoneda functor. So this functor, so you take the Hom of the generator with the brane of interest. That's what turns this guy into a module for the algebra A, for the endomorphism algebra of the generators. So you need to find you need to translate your geometric brane into a module for the algebra, and then you need to find the resolution of that module. So both of these problems are generally solvable only in principle, but not in practice. The first problem, okay. So it turns out, in our setting, we can solve them both at once, thanks to the fact that the branes we are interested in are products of one-dimensional Lagrangians. So I'll describe only the two simplest cases when the Lie algebra is either SU2 or GL1/1. The former theory will give us categorification of the Jones polynomial the latter, the Alexander polynomial, and Elise Lepage, who's a key contributor here, will tell us tomorrow about how to do the general case. So in both cases, the Lie algebra has a single simple root, which is fermionic for GL11 and bosonic for SU2. So both theories are based on the same symmetric product of D copies of a Riemann surface. The difference is that in one case you have the difference is that for SU2 the theory is bosonic, so there are some fibers that are not written here, and what's the potential and the holomorphic form. These fibers you can trade into the vector bundles that branes get equipped with. So the objects are Lagrangians, which are products of one-dimensional curves that you take to be non-intersecting, equipped with these local systems for the SU2 case. So given the link, we get a pair of such branes, a pair of branes, one that corresponds to the caps and the other one to these braided caps. So in both cases, the branes that are associated to caps are these simple intervals that you see. There's nothing else. They're products of these intervals. For the cap branes, the cap branes will be products of closed curves whose homology class is proportional to the class of these braided caps, but not equal. So for the SU2, the cap branes are actually products of figure-8 type branes. And for GL11, they're products of ovals. So the link homologies that start out as cohomologies of a Floer differential, acting on the vector space spanned by the intersection points. But what we want to do is we want to describe these braided figure-8 branes in terms of the generators. So how to do that? So you can describe the story in parallel for both theories. So as a warm-up, we'll start with the D equal to 1 case, when the target is just based on the single copy of the Riemann surface in both cases. And that's fundamental to everything that follows. So if you have two one-dimensional Lagrangians that intersect over a point, you get a new one-dimensional Lagrangian by taking their connected sum over the intersection point. Okay, so from the pair of these branes intersecting, you get a new Lagrangian. As the object of the category of A branes, or the smooth brane is equivalent to a complex of these two building block branes that's known as a cone of the intersection point. So these two pictures, this one, when you keep track of the differential, and the smooth brane are equivalent as objects of the category. Nobody can distinguish them. So if your target is one-dimensional, then taking cones over morphisms has a geometric interpretation as taking connected sums. So consider, for example, the cap brane in the SU2 theory that looks like a figure-8. So we'd like to describe it in terms of the generators. You want to stretch it out. So here we stretched it out. I drew a stretched out version in blue. So now it's clear that it looks like the generators where we take the connected sums over points at infinity. Okay? So if you keep track of the open strings that you get at infinity, the topology of the brane is the same. So now each intersection point at infinity is a specific element of the algebra with definite equivariant and cohomological degree. And to write a corresponding complex, you start with any one of these generating branes in code which maps you find at infinity as you go around. Okay? And then you can reorganize the result by cohomological degree to get a complex that resolves as figure-8 brane with a differential that squares to 0. The cap brane in the GL11 theory is actually even simpler. It's a direct sum of just two of the components of the generator, with the differential that also squares to 0 just by the algebra relation. The difference between the two cases, for ordinary Lie algebra, you get an ordinary complex. For Lie superalgebras, you get a twisted complex. Okay. This complex has, the differential has maps going both ways. It's a twisted complex. So more generally, so this is a baby example. More generally, the branes of interest are products of one-dimensional ones. So what we'll do to find their resolution is we'll work in the complement of this diagonal divisor, which throws out all the holomorphic maps, which are not simply products of one-dimensional maps. Having done so, the complex that describes the brane as the object of the category is simply a product of one-dimensional complexes. And those are elementary to find. It's just algorithmic. It's a game you can teach a kid. So geometrically, each map in this product complex is a cone over intersection. Because it's a map in a product complex, necessarily it looks like something non-trivial in one place and identity everywhere else. And it describes a cone over intersection point that's, well, identity everywhere except in one place. So having found the complex that resolves the brane in the complement of this interesting divisor, finding the complex of the branes you actually want is a deformation problem. It's a specific deformation problem because we know the algebra. And so you get a precise algorithm that you can run in principle. So the details of the algorithm, Elise will describe tomorrow. You can run for arbitrarily complicated branes, starting with products of one-dimensional complexes, which are elementary to write down, and running this deformation algorithm, which is iterative in these deformation parameters. So this generalizes to an explicit algorithm for computing arbitrary UQG link homologies. So a theorem with Elise and Miroslav Rabchak is that, in the paper that had appeared, is that for GL11 and SU2, the resulting invariants are link invariants. I should say that even though Hegar-Floyd theory has been solved, people did not solve it like this. So the solution is new. In fact, it's motivated by the SU2 solution, though we borrow some of the results they found. All right, so to prove you get link invariants, you need to prove that your invariants satisfy Markov moves. Now, our move turns out to hold as a consequence of equivalences satisfied by these braided cup branes. It turns out that proving all the Markov moves amounts to proving these slide moves, that you can swipe any one of the generators past your cup brane, okay, up to some degree shifts. Now, since we know the resolutions of branes on both sides, these equivalences are easy to prove and they're in fact homotopy equivalences of underlying complexes. What's important is that they're homotopy equivalences only in this more complicated theory with the divisor filled back in. Okay? If you delete if you delete these interesting divisors, you'll get a theory that's going to have the same Euler characteristic, but it's not going to give you link invariance. Okay. So in the SU2 case, the theory reproduces Covenant homology. The part that reproduces Covenant homology is a consequence of a theorem Ben Webster had proven, even though our formulation of it is nothing like what Covenant did. And strikingly, it reproduces Covenant homology, including torsion. So for example, if you take the trefoil, you get a following pair of branes. So you write the resolution of this blue brane in terms of the generators, and then you take the Hom with the, having done so, you get some very large complex of the generators. Having done so, you take the Hom with just this, with the interval branes. Out of the whole big complex, it's only going to pick out the parts of the generators that have intersections that are dual to these I-branes and forget everything else, and cut down a complex of objects of your algebra, or if you want, complex of A modules, down to an actual ordinary complex of C vector spaces. The complex that you get this way is 18-dimensional, which should be compared to complex that Kovanov gets, which is 30-dimensional. In fact, the very same complex, if you just, In fact, the very same complex, if you just think of it as a complex over Z instead of C over C, reproduces Kovanov homology, including its torsion elements. So there's a Z2 group here. Now, in fact, the swiping move can be used to simplify the brain you get to an equivalent but much simpler one. So this is the brain you start with. Using the swiping move, you can make it into this much simpler brain. And then the resolution gives you a complex that's only 6-dimensional. That 6-dimensional complex is the minimum possible complex you can write down to get homology that includes a Z2 torsion element. So the homology has 5 elements, including torsion. So the theory that I described extends to arbitrarily simple Lie algebras, as well as Lie superalgebras. So we are currently developing a SAGE code whose input is an arbitrary link, a choice of a Lie algebra and its representation, the color strength. Right now, they're minuscule representation. Minuscule means that all weights are in the single orbit of the Weil group. So, for example, for SUN, all fundamental representations, one for each node of the Dinkin diagram, they're all minuscule. Anyway, whose output is the link homology. And as part of the package, you also have means of just proving on the computer that, proving these slide moves that prove that your theory gives, that you use to prove that your theory gives link invariance. And by now we've done things like, at least we'll tell you what's the current state of the art. So, okay, that's it. Thank you. Yeah. Mm-hmm. Oh, so any questions? I thought you asked this. Okay, I can ask. So any questions? Yes.
What are the associated dualities with the A-branes?
Can you say this again?
The associated dualities with the A-branes.
Oh, what is the beginning of your question?
What are the associated or the type of dualities in the A-branes?
The dualities with the A-branes. Could you rephrase your question because I don't understand it?
For example, the D-branes are a very usual example. We use two-duality to transform from a D-brane, like from D+1 to D or D-1.
Right.
Is this even a legitimate question?
Well, a homological mirror symmetry is an example of such a duality, but it will take one category of branes to another. Right? So T-dualities won't take that category of branes to itself. If you want, the kinds of dualities that this category has come from the action of braiding. So as you move punctures around, the whole category stays the same, while its objects get permuted, right? I mean, people often study what happens to, to objects as you pass through walls of marginal stability and what have you. Though that action of braiding is that, and in this setting we can describe all of it because we know it explicitly. There's a question over there.
Do you only consider the Lagrangian A-brane, or you also include the coisotropic brane?
No, just Lagrangian brane.
It's Lagrangian, okay.
Any more questions?
So let's all thank Mina for the
Actually, I want to
talk.
say something. There's a part of this that I didn't tell you about, which is where do these target spaces come from? So if you take ordinary Lie algebra, the full target space, you should think of it as a Coulomb branch of the four-dimensional gauge theory in a circle, gauge theory that's directly related to this representation theoretic data. In fact, its mirror is a Coulomb branch of a three-dimensional gauge theory in a circle with the same quiver. Okay? So the actual spaces are, for the quintic, we weren't able to do this kind of thing. It turns out the places to look if you want to study categories of branes is Coulomb branches. Okay? What's even more interesting is if you want these superalgebras, then on the B side, you get a Coulomb branch of a 3D n equals to 2 theory. Now, we don't usually think that 3D n equals to 2 theories are good theories to study, but there's a class of 3D n equals to 2 theories which are related to representation theory of superalgebras, which are as nice as the n equals to 4 counterparts. In fact, the reason you would think that it should work, that such a thing could make sense, is that in the n equals to 4 setting, we explicitly break the n equals to 4 supersymmetry down to only n equals to 2, which is the structure that representation theory uses, right? This is what means, otherwise you get a theory that q is equal to 1, which is extremely boring. So making q not equal to 1 means you've actually broken n equals to 4 supersymmetry, which is just n equals to 2, okay? And the A side spaces are mirrors of these 3D n equals to 2 Coulomb branches. The theory also has extension to Fermat modules, so infinite dimensional representations, which would give you knot complements. And so forth. So, great, thank you.
Thank you, Mina, for the question. And I understand there's coffee and cookies outside until 11:20.
Yes, there will be a break in the terrace, and we can reconvene at 11:30. Let's reconvene.
Yeah, I think it's on, right?
Yeah, perfect. Yeah, perfect.
Okay, great. Okay.
Yeah, we will start in a few minutes.
Yes. Yeah. Oh, yeah. Yeah, I think I have enough chalk, yes. Yeah, let's see. Sometimes I might want to different colors, but let's see. Yeah, colors. Yeah, I think there are colors here.
For the outside.
To let the people outside know that
Oh, I see.
Probably to hold the people from outside.
Hi, Alessandro. Yes. Yeah, ciao. Yeah, thank you. Yeah, thank you so much for organizing this. Yeah, yeah, long time no see, and especially after the COVID. But yeah. It's as always. It's.
I see you training.
Not exactly, but.
Good.
Yeah. Great, fantastic. Yeah, I'm sure it's.
Already in Italy, no?
Yeah, that's right. I was in Florence, yes, for a couple of weeks, and there was a program. Yeah.
Green light is
It's a very long time that.
That's true. Yeah, somewhat surprisingly. So at some point we were seeing each other like every year, but.
Yeah. Okay, let's see. Maybe.
Yeah, but I have more duties, etc. But nice seeing you. Great. Yeah, we should check the yeah.
Yes.
Oh. A little bit hard to see, maybe. Yeah, I think 10, yeah, that's right. 15 minutes, right? 5-0. Yeah.
I'm going to show you that.
Yes. Like 10 minutes before or 5 minutes?
Yeah.
10 minutes, 5.
2010.
Oh, 2010, 5. Okay, sounds great. Yeah. Yeah. Yes, of course. Yeah. Yes. Maybe 2 minutes. Oh, hi, Julio. Yeah, yeah, nice to see you again. Nice to see you again. Great. Yeah.
So for our second talk this morning, we're pleased to have Masahito Yamazaki, who will talk about 3D n equals 4 theories, quiver varieties, and vertex operator algebras.
Okay, let's see, is the microphone on? I think it's on. Maybe I should make it closer. Is it better now? Or maybe not, so. Well, let's see, why is that? Right in the middle, center, okay. Here. Okay, is that better? Somehow it feels it's not the best, but hope everybody can hear. Okay, good. So please let me know if you don't hear anything. Also, yeah, this time I'm very tempted to use the blackboard. Well, this is a party meeting of mathematicians, and so I'm very tempted to use this actually very beautiful blackboard. And of course, let me thank the talk by thanking the organizers. And actually, just like Amina, I came to ICTP as a graduate student. In fact, it was one of my first trip to Europe as a graduate student. And ever since I've been here, and also to Trieste many times, it's always a pleasure to be back. Now, so this is a conference about mathematical physics, right? So it's an interaction between mathematics and physics. Sometimes the development in mathematics motivates the development in physics and vice versa. But it's actually also true that sometimes, for example, through physics, different branches of mathematics are connected. And so actually, even from a purely mathematical viewpoint, the interaction is pretty useful, and vice versa. And that's a general theme of my talk. And that's reflected in the title. So this talk is about 3D n equals 4 theories and the relation between quiver varieties and vertex operator algebra. So quiver varieties, vertex operator algebras, they're mathematical well-defined concepts. But we're going to see that there is a very nice parallel in between them. And we're going to extract new information from there. And this work is in collaboration with my excellent collaborators, Iwano Koman, Myunbo Sim, and Ihao Tso, who are or used to be the postdoc at my institute. And the one thing to note is that this is based on a paper which appeared last December in physics. But actually, the physics paper contains some theorems and statements. And also, we are preparing yet another paper in pure math. So hopefully, depending on preference, you can have a look at either of them and try to enjoy it. Yeah, so let's see. So let me today begin with the first general introduction. And well, let me first start with the quiver Q. I try to write reasonably large. So, or maybe this is too large. So quiver is just vertex and edges, just in case. Let's see. And then also we associate the dimension vector B and W. So I just saved a little bit of time by drawing a board. So we have nodes. This is the quiver, but there are also frame nodes, which are represented by squares, which is the standard notations. And you associate the numbers, dimension vectors, B and W. So that's Nakajima's notation. And so this is the defining data. So I keep using Q, B, and W. And this data is the defining data for three-dimensional n equal 4 gauge theory, if you're a physicist, gauge theory. And well, this data is Q naught, the vertices is like n equal 4 vector multiplet. So it's represent the gauge group. So the gauge group is like a product of, say, if it's SUN or UN, let's say UN BI. Does it look okay? Yeah. Okay, I think it's okay. And then there's a Q1. So this is edges, arrows. So this is n equal 4 hypermultiplet. And then there are arrows, and I'm sure that a lot of people have seen this already. But if there are arrows in between, for example, it's in the bifundamental representation. So okay, it's a standard definition of the quiver gauge theory. And then one nice thing about it is that once you have this theory, it's a physical theory, but you can extract different mathematical ingredients. So one is one such thing. Okay, maybe let me write it here. One such thing is the quiver variety, Nakajima quiver variety. Okay, so what is it? Well, Nakajima quiver variety in the physics language is the Higgs branch of the moduli space, vacuum moduli space. Let me write M Higgs, and I'm going to write it as MQBW. I'm going to define it later, and then on the other hand, there is also a different concept, which is the vertex operator algebra, and it goes by the name H over A twisted vertex operator algebra. Boundary. Vertex operator algebra. So I'm going to denote it by B of the dimension vector, Q and dimension vector. Okay, so how to extract this? Well, the basic idea is to go to the boundary. So this is a three-dimensional theory, and you can try to go to the boundary. But first of all, this is three-dimensional four supersymmetry. You have to specify what boundary conditions you talk about, you choose. You preserve the boundary condition, which is half, 0-4 supersymmetry, etc. But the details doesn't matter for the purposes of my talk. It's just that you have a 3D theory, and on the boundary you have a 2D, which is described by this BOA. And now there are two different types of boundary conditions. Well, actually there are more, but two different types of boundary conditions, which are called A and B type. A and B, as you are familiar with the mirror symmetry, and I'm going to consider the A type. The previous talk is actually with the Coulomb branch, which is the other B-type boundary condition. But in this talk, I'm going to consider A-type / Higgs-type boundary condition. And then the statement that you get non-trivial BOA starting from this three-dimensional four theory. Now, well, let's see. So this is enough. But another way of saying that is that if you start with three-dimensional four theory, so this is a physical theory with a gauge coupling constant, etc. But you can also go to 3D theory, 3D TQFT. By the topological twist. This is, well, let's see, again, there is A twist, B twist, but let's say A twisted TQFT. And once you have the TQFT, you can also go to the boundary. So, and then that's how you get a BOA. So this is like a generalization of the celebrated correspondence between Chan-Simons and West-Middle model on the boundary. But it's a more involved one. This 3D TQFT, for example, partly because this thing contains many extra matters, scalar fields. So it's not, for example, pure Chan-Simons, but more things. And in particular, contains local operators. And that means that there is an even richer structure on the line operators, point-like defect inside the line operator. So there are even higher categorical structures and non-semi-simple TQFT, etc. There are a lot of structures. So if you're interested in knot theory, etc., this is what is underlying here. Although I'm not really going to talk about 3D TQFT, but just concentrate on this particular BOA. Now the question is that the natural question, if you look at this picture, is that what is the relation between, first of all, what is this BOA? I just wrote it abstractly as BOA. Is there a procedure to specify it? And also, can you identify it? Like what are the generators or central charge or et cetera, et cetera. So that's a very concrete question. And in fact, that question has been addressed. I should say that, so this is the Blackboard talk, so I apologize, I'm not going to list that many references, in fact, very few references to save time. But at least I should say that this type of discussion is initiated by Costello and Gatto, Kevin and Davide, and there are many people who have worked on this. In particular, Thomas Kreutzig, Tudo Di Mofte, Nick Garner, and many other people. Sorry, I don't name everybody. But let's see. And so it's an interesting subject on its own. And so far, most of the development happens for abelian gauge series. But I'm going to, what my interest is partly about trying to understand the connection to quiver varieties, general quiver varieties. So I want to go to the non-abelian case and then discuss the associated BOA. Now, one question is, of course, how to understand this. But there is another question as to how to understand the relation between the two. Right, so it sounds like a natural question. Well, a priori, there are different objects, but it turns out that there is a very close relation. So the motto is that if you start with a quiver variety, you can chiralize. So make it holomorphic, and then you get this A and H twisted boundary condition. Although with a lot of subtleties, actually. So in fact, clarifying that it's, but at least the motto is that you kind of uplift it, and you get a BOA. So quiver variety uplifted as a BOA. Now, you can also try to go the other way around. And that's also a very subtle story. And part of our interest is to try to prove the statements. But at least at the zeroth order, there is a concept of associated variety. Associated variety. And if I have time, I might comment just a little bit on this. But there is the statement is that you have a BOA, there is an associated variety. There's some variety, geometry. And then so roughly speaking, if you start from here, and then you can go extract the geometry and then go back there. That's one definition of colorization. So the goal of my talk is to try to understand first the relation between the two. And I'm going to explain the story, in particular this construction of BOA, in such a way that the parallel with this is extremely clear. And then I'm going to study this BOA itself, and in particular, connection to the double algebras, and free field realizations, or Mueller transformation, if you like, free field. Free field realizations. So that's what I'm going to talk about. Okay, hopefully things are clear. Okay, now let's try to discuss the first quiver variety side. Now, I'm sure that many people have seen the definition of quiver varieties, and I'm going to comment very little about that. Only the minimal ingredients needed. So, okay, so let's come to the quiver variety. So, okay, so what are the quiver varieties? Well, it's defined by hyperkiller quotient of something by some group action. So you need to first show what are the starting object. And the starting object I might write as a lep of the quiver, QBW. Okay, so what is the, so you regard the quiver as the set of collection of vector spaces located at each point. So here I have a little bit more messy figure. So if you have V1, you have, for example, here you have V2, and you have a vector space of the V2 with dimension small v2. And you have the, again, similarly, the vector space. And then, of course, these arrows are morphism. It's in between. And in particular here, there is a notation. So there are arrows between different vertices. And the arrows coming to the right, I call X. Y called Y. And then there are also arrows coming from the squares, framing nodes. That's denoted by alpha and beta. So these are the data. So roughly speaking, these are like alpha xi, yi, and okay, so I already capitalized it. Okay, xi, yi, which is not a good notation, but okay, alpha beta I. And then, yeah, so the collection of these. These are just a cotangent of lep. That's what I mean by that. So it's just a collection of matrices, if you like. Now, there's action of the GLB, what I like GLB. So this is the complex equation of the gauge group, GLBI, I at the associated vertices. And so it acts on the space by conjugation by matrices, of course. And then there is a concept of the moment map. There is an ice moment map associated with this action. And this takes the form of xyi minus yi minus 1, xi minus 1, plus alpha I beta I. So you can check that, for example, xi yi, let's see, sorry, xi yi, so that first goes to, oh, sorry, this index was wrong, yi, and come back, for example. So if you're starting with that vertex, you can go around. There are three ways of going around, and they all appear inside this moment map. And then once you have this moment map, I think you can see even when right here. And then there is a quotient. So that's defined. So that's the definition of the quiver variety. So this is M, whereas this is mu inverse 0. And then I impose a stability, etc. But then there's the GOB. So this is the definition of the Nakajima quiver variety. And if you like, you're also, I can also define an extended version where the values of the complex moment maps are also regarded as part of the coordinate. So this is copies of C for each vertex. So for each vertex, there's a FI parameter, if you like, and those you regard as part of the coordinate. So this is the minimal definition of quiver variety. Okay, so now I'm going to chiralize the story. or going to discuss the BOA version of this story. How does it go? Well, the basic idea is actually very simple. So here, these are just the matrices, right? So, and, but I'm going to promote these matrices into fields of the BOA. That's the motto. So let's categorize into BOA. Let's see. So the first ingredient, well, I'm going to emphasize the parallel with the Kuiper variety story, although there are important subtleties which we'll come to. But first of all, before the reduction, it was just a collection of matrices, and then we have the simple ingredients. I'm going to define B sharp. So this is a BOA, defined from the data of the QBW. So this consists of several different ingredients. The first is the free beta gamma system. Free beta gamma system, and these are promoted to xi, yi. And yeah, I think alpha I, beta I, the counterpart alpha I, beta I. And except that these are, it almost looks like, okay, alpha replaced by I and j. Sorry, maybe this is not good notation. But the point is that these alpha x and y's are beta gamma goals. So what it means is that this itself, for example, it's a matrix. So it has a matrix index, yi, gamma delta, etc. And then impose the relation, like y, x, and y, w. So this is equal to, okay, so I need to write down the indices too, alpha beta, yi, w, gamma delta. So this is like a 1 over 1 minus delta, and there's delta ij. If you like, there are also contractible indices. So this is just a simple free beta gamma system. So for each arrow, you're going to associate the free beta gamma system. And for each arrows in the opposite direction, we have some relation like this. Now, you're going to write down something afterwards, but let me first proceed to the next ingredient. So this is the counterpart of this T star lep. Now, there is a counterpart of this thing, in this of the action of the group. So the action of the group comes from the fact that the Higgs branch has an action, and that comes from the fact in physics language that means that there is a Fravor symmetry. Now, when you have the Fravor symmetry, there's a background gauge field you can turn on. And if you go to the boundary, you get the vertex operator version of the algebra, which is the Kac-Moody algebra. So there's a statement is that there is a current of the Kac-Moody algebra, which you can write down. So at each vertex, U and I, so U and I current. And this takes actually exactly the same form as this formula. So you just promote this to fields. I'm going to write down the same thing. xi minus 1 plus ji. And yeah, there are going to be corrections, but that's the idea at least. Okay, so that's the current. And then once you have the current, you can do the counterpart of the symplectic reduction. And in the BOA, there is a reduction procedure associated with the gauge group, which is this BRST reduction. So you're going to do the BRST reduction. Or if you like, if you're more mathematics language, it's a relative version of the semi-infinite cohomology. Well, semi-infinite means something like Dirac C. So, but in any case, there is a BRST reduction in semi-infinite cohomology, and that's what we're going to do. And in order to discuss that, first, you need to include BC ghost. Okay, so these are the BC ghosts. And then, so it's essentially the same commutation relation as this, and except that these are, of course, fermions. And then once you have the BC ghost, you can write down the supercharge. And there is a canonical formula for this, which is like exponential super I. And then there is this the current. So you combine all these currents So let's call that JB star. And then there is a half times JBC, where this is the current associated with this thing. Well, the formula doesn't matter for this purpose, for this talk, but I can write it down. So there is some BRST operator like this, which you can write down. And once you have the BRST charge, which squares to 0, then you know what to do, which is to take cohomology. So that's BRST cohomology, or semi-infinite cohomology, and with respect to the supercharge. So that you can write, and in the mathematics notation, you write this as this thing, and this GLB action with respect to this vertex operator algebra. So that's this thing. Okay, I forgot whether to include the BC in the notation, but anyway, the meaning is clear. So you just add the BC ghost and then do the BRC reduction. That's the story. Except that there is some subtlety. So of course, for this BRC cohomology to work, you need Q squared to 0, of course. But the question is that, is this actually the case? There is already a formula, and I have essentially told you all the OPE, so you can just compute it. And it turns out that it's actually not 0 in general. So it's not 0. So you cannot define the BRST cohomology. Something is wrong. Now, there is actually a physical counterpart of the story. So I said that these 2D BOAs are the boundary theory of the 3D theory. Now, when you start with the 3D theory and go to the boundary, in general, there are anomalies associated with the boundary, which means that you have to cancel the anomalies. And you need to incorporate, so that you can do by incorporating some extra matters localized on the boundary. And another way of saying that, purely BOA way of saying that, is that this Q doesn't square to 0, so you have to add something to make it 0. Let's see. Yeah, so more technically speaking, the JJ has a commutator, sorry, OPE, and JJ OPE has a double pole, whose coefficient is proportional to the level. That's like a quantum effects, and that spoils everything up, because if you have a double pole, you want to take a residue. It's more complicated. In any case, you have to do something and add something extra. And in the physics discussion, so this is UN, and there is a UN part, and UN can be decomposed SUN part and U1 part. It is called the SU anomalies, the U anomalies. Now, what about the SU? Well, first of all, let's discuss the SU anomalies, SUNI anomaly. But as it is. And so what are the, let's say, anomalies? Well, for SUN anomalies, there is actually a way, well, first of all, the first comment I have is that there is not a unique way to cancel the anomalies. So you can have complicated thing, for example, complicated 2D theory to cancel the anomaly. And the choice is not at all unique. And depending on the choice, different choice, you get a different boundary BOA. However, you can also try to look for canonical or choices of canceling the anomaly. And there's one way for SUN anomaly. So this is canceled by incorporating, including boundary, 2D, boundary means a 2D, free fermion, fermion. So in the BOA language, it's like a fermion. If you're worried about supersymmetry, it's a fermion multiplet, fermions. And the copies, and how many fermions? How many fermions you need? There's a formula for that, which is that Wi plus Bi plus Bi plus 1 plus Bi minus 1 minus 2Bi. And yeah, so I'm going to write this as a W, so D equals to W minus CV, where C is a Cartan matrix. So I forgot to say that I'm going to consider linear quiver chains, although some of what I'm going to say generalize to more general quivers, etc. But let's say I'm going to discuss the linear chain of this type, and the C is the Cartan matrix. So this is the same expressions. Ni, sorry, where is Ni?
Yeah, I'm just confused. You have J sub UNI current.
Yes.
Your alphas and betas and so on are going from 1 to NI.
Sorry, yeah, indeed, sorry.
Is that VI?
Yes, sorry, NI is VI, sorry.
Okay.
Yes, indeed, NI is VI, sorry, yes. Yeah. That's right. So yes, thank you. Thank you for asking. Anything else unclear? Oh, okay, there's another one there. Okay, so, okay, I see, in the anomaly. Oh, sorry, okay, in the blackboard, it's, if you're sitting in front of the blackboard, it's, okay, I see, good, thank you, yes. It's a little bit hard to see when you're in front, like that's a typical thing for a teacher. But in any case, let's see. So, well, first of all, you need to add this thing. So you need to assume that this is 0 or positive. When it's 0, it's called a balance. It's positive. You can cancel the anomaly this way. And this condition, if you know, is the same as the Gauss-Witten's good classification for good theory, condition for good theory. Okay, so what about the U1 anomaly? Now, for the U1 anomaly, there is one way to cancel, one minimal way to cancel it, is to include the Heisenberg. Hi for each vertex, such that they have the OPE, I think you can see. So OPE is the HI of Z is equal to Z minus W squared times Cartan matrix. So that way, that's the minimal way to cancel it. So actually, so we need extra ingredients, which is like a free fermion, DI copies of free fermions, which I might write 5 psi, for example, and then Heisenberg. So these are the extra data. So I emphasize the parallel with the Kuiper variety, and that's inspiring. But also there are some subtle differences. You have to add extra ingredients. So even the defining data requires extra data. And then once you do this, you have to modify it, phi I minus psi I. And if I remember correctly, you have to put in the generator. So this is the identity component. So this is the matrix. So you write the diagonal part to be the Cartan. And so it's actually interesting because you see that this HI is like identity part. So this is an analog of the value, the chiral BOA counterpart of the value of the complex moment map. So let's see, there are extra subtleties, but the story goes well, and it works. Okay, so once you have this, you have a definition of the BOA. Now you can ask the question of how did it look like, right? So. Okay, I think I have 30 minutes. Yeah, not 20, right? So, oh, yeah. Sorry, it's like a 30 minutes or 20? Okay, 20 minutes, yeah. So, okay, so let's see. It's 20 minutes. So, okay, so what other theories look like? Well, okay, then I need to speed up a little bit, but let's see. Nevertheless, I'm a down-to-earth person. So before coming to a general theory, it's nice to talk about a very specific example. And it's this theory. It's an example of a balanced quiver. Hope it's quiver, yes, 2. So for example, I can take a quiver of this type. Well, first of all, everything is explicit. So what you can do is to try to run the BRST charge, everything is explicit. So if you want to go to the BRST, well, of course, it's defined by BRST reduction. You need to find a nice operator which is invariant as BRST charge. So you can try to be hands-on and try to look for that. Now, let's see. So what is the way to look for that? Well, there are some operators which you can write down. Well, for example, if you take I1 itself, it's not at all BRST invariant. It has indices, and indices don't transform non-trivially. So you need a little bit more to make it work. Now, there is, for example, some canonical, let's see, at least method for trying to guess what the operators are. For example, you can start with this vertex. And first start with this I1 to go up, and then go to the left, which is like a Y1, and then go down, for example, J2, for example. Now, it's like going around the path, and it's a gauge invariant. So this is actually how we see the correspondence to the Higgs branch. So Higgs branch are parameterized gauge invariant operators, so this corresponds to path, right? So I just do the BOA version of the same thing and write down the operator like this. Now, you can also write down the same thing in the opposite direction. So you can also go in this direction. So that's like, okay, what I should do? First, okay, so if I want to, 2 from there, then I need to first I2. But then I need to take x1 and then j1, or anyway, so maybe you're getting tired of indices. But in any case, it just simply corresponds to the path going the other direction. Now you can try to go, for example, there is actually a similar one, but staying at one of the vertices. Yeah, it can be, let's see, so, and then that's this one, j11. And in fact, this one is particularly simple looking, because this is also another path, which just going back and forth in between here. That's another cross path. So you might write out the formula like this. But actually, this itself is not gauge invariant. You need to add the Heisenberg contributions. Which is the extra contribution. So the moral of the story is that if you have a coordinate on the Coulomb branch, you can more or less uplift it to the fields of the VOA, except that precisely because there are extra subtleties in the defining data, you have to correct it a little bit. But, sorry? Oh, sorry, did I say Coulomb branch? Sorry, Higgs branch, yes, sorry, yes. Higgs branch, yes. Well, of course, if you go to the mirror, it's a Coulomb branch, but yes, Higgs branch, yes. So you are in the yeah, these are coordinates. And now you might think that there are many other paths, but it turns out there is a momentum up relation, and so not everything is independent. It turns out that these all three are what's necessary. Now it turns out that if you have the three data, the interesting thing is that if you take this and take some appropriate combinations, it turns out that together with you need to add value of the fermions, etc. But in the end, you can map it to strong generators of the W algebra of GL4 and the minimal nilpotent orbit. F minimum means the minimal nilpotent orbit of the W algebra. So this is okay. So this is not exactly so, but essentially by reshuffling the generators, and then you can arrive at the W algebra. That we can check explicitly. If you look at section 5 of the paper, we have detailed computations, and then so there is a statement that in this particular example, there is embedding. Sorry, there is a homomorphism into the vertex operator boundary BOA we are starting with. Except that W algebra is not everything. There are many other generators involving the fermions, etc. So this thing is even richer than this original W algebra. Now, this raises many questions. Well, first of all, if there is a W algebra, can you try to find some nice structures? Well, first of all, I didn't guess what type of W algebras you might expect for a more general quiver rather than this, for example. And also, for example, if there's something else here, then what you're going to it's not just a W algebra, but something more. And how you study this? Well, in principle, you can have the fermionic generators and things like that, and that's actually what we tried. But the formula looks increasingly complicated, as is often the case in this BOA. So we need a systematic procedure. Now, in the remaining time, I'm going to try to explain that systematic procedure. And the idea is that, I would call it the localization of quiver BOA. Okay, so what is the idea? Well, the idea is to try to appeal to the intuition between the geometry, the quiver variety, and then there is a counterpart, this vertex operator. So this is BOA. So this is a quiver variety. So it's a geometry. Now, the boundary BOA is complicated, but of course, the quiver variety itself is also complicated. So the question is that, is there a way to understand it in a simple way? And this is a variety. So one of the procedures is that, well, you can go to a local patch. So this is algebraic. So if you take some polynomial, so this is defined by the region where polynomial is non-zero. You go to an open set into the Zariski topology, and then we are in a smaller space. And you can keep going to even smaller spaces, etc., and it becomes even simpler. Now, there is a counterpart of this in the BOA. So this is more like the ring of functions on this variety. So if you have this type of procedure, you can actually, there is going to be embedding into another BOA. And then you can keep going that. And at some point, you expect that the geometry is so simple that the procedure terminates at some point, and you have a free BOA. And if you take advantage of that, that means that the whole thing is embedding into free field. So you expect the free field realizations or Miura transformation and their generalizations. So this is the idea. Now, how to do that? Well, one of the systematic ways is to consider, so you need to do something at the BOA and apply the procedure of restricting the patch and things like that. And there's a very nice way of doing that, and that uses the idea of C4 BOAs. So you can consider C4 BOAs. Okay, so C4 BOAs, I'm afraid that I have no time to even remotely comment on that, but at least it's a sheaf, which means that for each open set, like this one, there is associated BOA and satisfies some compatibility conditions between the open set. And then you can define some C4 BOAs such that in some region, so okay, what is F? So this is like, and then you expect some simplification to happen. So you expect a C4 BOA. And let's see. And then once you have the C4 BOAs, you can, well, it's most strictly speaking, it's called the H-bar addict BOA because you have to you're taking the inverse of the fields. You have to worry about the convergence, which concept was introduced by Arakawa and collaborators. And then once you have the C4 BOAs, you can take a global section. And that defines some BOA. So this is a global section. And H-bar is not necessary, so I can set H-bar to 1. So this is the global BOA. And in fact, precisely because this one behaves nicely under this type of operations, you can show that this has a free field realization. Yeah, so let's see. So the statement. So the theorem, one of the theorems is that, well, so this algebra, sorry, here is, I don't need the H-bar. H-bar is set to 1. So this M, well, actually I consider M tilde, which is the extended quiver, which I defined earlier. And then this has embedding into beta gamma system. Well, in the language of this notation, you get the T star of C n slash M times some Heisenberg, copies of Heisenberg at each vertex. So there's a formula for n and m, but I don't remember it now, so I'm not going to write down. It's in a paper. So these are integers. And these are also levels, which you can compute a priori. And then these are like a Heisenberg. And then, so these are the beta gamma system. So that's one of the statements. And in fact, this is an explicit, well, it's not like an existence statement. There is a precise algorithm. So the procedure is that you're starting with a quiver. And then there's a procedure for eliminating that to make it a simple quiver. And they keep doing that. In fact, essentially, in the process, it's somewhat like a confinement, actually, that you remove the gauge node of the quiver. So in each process, you keep removing the gauge node of the quiver. At some point, there is no gauge group. So you get a simple theory. BRC reduction becomes trivial, and you get something like this. And you can work this out very explicitly. And then, for example, in some examples, you can show that, for example, in the examples we discussed before, where there is a double algebra, you can apply this procedure and then try to see what type of field realizations you get. And it turns out that that's what you get from the Wakimoto free field realizations. But this one is much more general. So you can do a variety of quivers and very systematic procedure for writing the free field realizations. Okay, yeah. So that's the thing. But now I have just a little bit of time, so let me try to fill in one missing point actually in this discussion. So here, it's actually, you notice that things are subtle. The reason is the following. So okay, I declared that I was interested in studying this BOA, right? So that's what we wanted to study. And then I say I invoke the gadget. Yeah, so this is so there's C for BOAs, and define some D, and it has a nice free field realizations. But a priori, this D can be different from this B, which I wanted to study originally. And yeah, it's actually a very subtle question. So the difference is that here, I take a global section first and do the BRC reduction. But here in this business, you first do the BRC reduction locally, and then take a global section. And there is no guarantee that they commute. So they might not be isomorphic, for example. And so the question, there is a question hanging around that what is the relation between the two? And we certainly don't know the final answer. But at least there is one particular statement we're going to show in the second version of the series, which is this math paper. So this is a theorem. So there are two assumptions. Assume, well, first of all, I defined previously that di equals to wi plus bi minus 1 plus bi plus 1 minus 2bi is 0 or positive. So this is a good. I still keep assuming that. And then one of the following. And so these are the various different cases of the quiver. So for example, one is that the quiver is totally negative. So it means that the Q is complete, and so the Cartan matrix is negative, if you like, but complete and two self arrows at each vertex. So this is one case. Yeah, you can have, for example, two nodes, for example, and then there should be at least two nodes, two arrows here. It's a little bit weird one, which you usually don't encounter in physics, I guess. But and then it's a complete graph, so it's connected, something like that. Now another case is the dinking. Well, dinking I'm still assuming that it's a linear quiver, and or another more way of saying that is that it's almost the vertices are almost abelian, except at 2 points. Or maximally 2 points. So it includes the ability, well, let's see. Actually, Q is and then another is A1 quiver. And another is the Jordan quiver. So these are the technical requirements in order for the proof. And then the result, yeah, so this is also a theorem in a paper. And another theorem in a paper, this is by us, Z, is that there is a, well, first of all, there is you can show in general, there is embedding into this CIF version of BOA, the global section of the CIF version of the BOA. So there is always a homomorphism as a vertex superalgebra in between the two. And this is injective. Oh, sorry, I wrote the theorem. Sorry. Okay, I don't need to. Okay, maybe I should write it here. Then injective. We also have a related result about the vanishing of the negative part of the cohomology. But let me not write it now. But at least you can show that this map is at least injective. Now, once you have this, you can try to make the loose end, because first of all, originally you might be interested in this, but that's embedded to this CIF version of this, which now has a free field realization. And if this is injective, so that becomes embedding. And then this part is also embedding. And hence, you have a proof that's embedded into the free field BOA. So you have a free field realization of this guy. Yes. Now, I have 5 minutes, so I can comment a little bit on also the connection to the W algebras. Yeah, so, well, as I said at the middle, we have a connection of these two W algebras in some cases. But now the W algebras themselves are not these boundary BOAs. So in some cases, there is a morphism. But it's actually not necessarily easy to say in general whether it's injective or surjective. But first of all, but sometimes, for example, if you go through this bit, so this has a free field realization, so you already have this algebra. So you can just go ahead, and then this is mapped to the free field. And then you can check what type of free field realization you get. And in some cases, it coincides with the free field realizations known in the literature. In which case, we know that it's embedding. So in that case, there is also an injection. So you can make a connection to the W algebra. And okay, so which W algebra? Well, to properly explain that takes more minutes. But there is a cross of Quiver gauge series, which goes by the name of T rho sigma theory in the notation of Gauss-Witten. So in particular, the Higgs branch of this theory is a nilpotent cone associated with the transpose law, intersection with the Slodovitz size for sigma. And in this case, and in particular, for example, when this sigma is 1, 1, 1, so these sigma laws are partitions of n. And so when this is the case, well, and then you have the sigma only, and then there is an expectation that you get the W algebra associated with this nilpotent element coming from the sigma, and then you get the level Wn minus 1. Not a critical level, it's a little bit off, but there is a W algebra map into the vertex operator algebra. So there is still a connection to W algebra. We know in some cases, and we have some non-trivial checks for that. Now, I'm going to finish by saying that, okay, so this is a subalgebra. So, well, okay, I haven't checked that it's actually embedding in general, but sometimes it's a part of the story of the BOA, not everything. And, well, in that case, and so you can naturally imagine that is there any way to characterize this subalgebra inside this BOA? And I don't know the answer. I don't know the answer, except that there seems to be some connection to nice mathematics known as the Namikawa-Weil group. So this is related to the resolution of singularities, deformation of the symplectic resolutions. And in that story, Namikawa have a nice story where there is some version of the Weil group acting on the geometry. And you can talk about the similar version of that on this geometry. And so in that case, as far as I know, I don't claim to know much about it. But as far as I know, it's a permutation. And then, so the natural expectation is that the image of this is in the fixed point set of this thing under the Namikawa-Weil group. So it seems that there is some more story to be clarified, and along the way, the study of the geometry itself could play some important roles. So I guess my time is up, so let me finish. Thank you.
Hi. If I consider the D3 NS5 brane, D5 brane construction for this Gauss-Witten theory,
Yes.
What's the 2D boundary modes come from? Like this Heisenberg algebra and this zero coming to from a
boundary
multiplet?
modes, that's a boundary condition, so you have to, it's extra ingredient which you need to add. So it's not 3D theory degrees of freedom, but extra degrees of freedom localized on the boundary. Now, so for free fermions, you just include a Fermi multiplet. So that's a multiplet in 2D, preserving half the supersymmetries. Now, if Heisenberg, okay, so it's Heisenberg, it looks a little bit artificial, but you can also, if you if it's fine to add extra U1 current, you can also realize them by free fermions on the boundary. So the short answer is that it's not a part of the property of the theory, but it's more like a property of the boundary condition. And you need to, yes?
You have some description of your theory from like 10 dimensions or whatever,
Yes.
then reducing should give you also the boundary condition.
Yeah, I mean,
So as I think the question is, how do you learn that boundary condition from this reduction?
Well, let's see. I mean, here it's, let's see. First of all, it's not unique. You can have different boundary conditions. As long as it's compatible with the A twist and, for example, consistent with the supercharge, it works. So it's not, first of all, it's not a unique choice. That's comment one. And the comment two is that, okay, but if you're still looking for some nice interpretation, for example, well, you can, depending on whether you can go to 4D or 6D, et cetera. But let's say you do go to 4D. And then one way is to go to a cigar, 4D cigar. And so instead of having, so we have a 3D theory on the interval, right? So if you suppress the 2 dimensions, it's a boundary condition here. And then you can start with the, so this is a 3D theory. But you can go to the 4D theory on a cigar with omega background turned on. And then you can discuss the BOA at here. And in that setup, so that's just a 4D n equal 2 series omega background. And there's a nice paper by Yagi and G1O, which says that actually the setup is the same as what the Rasteri, Beam, and others do in the connection with constructed chiral algebra from 4D theory. So in that case, that's just omega background, and reduce it, that's it. And in that case, actually, but there are important differences, actually, because in that case, okay, what happened to the choice of boundary condition I have been talking about? Well, it's related to the fact that, first of all, in that case, people typically are interested in superconformal case in 4D. It's called a balanced, in this language, it's a balanced quiver, so there is no need for extra matter. Also, they're doing SUN gauging instead of UN, for example, so they don't care about UN normally. So because of these reasons, you don't really have to worry about it. The canonical choice is almost empty. And then that's how you get the boundary BOA in our case. But so you can sometimes go to 4D, but our discussion, at least as the defining data, is much more rich.
So Nakajima quiver varieties are famous for being hyperkähler. Does that mean that this vertex operator algebra is some kind of n equals 4 superconformal algebra?
Let's see. I see. Yeah, I mean, it could be. Yeah, indeed, the boundary conditions are 0, 4, for example. So it's consistent with supersymmetry. So.
Large or small n equals 4 superconformal algebra?
Yeah, that I need to think. But if I have to bet, well, it's fun if you get a large one, but probably not. But if I have to bet now. But yeah, but I think that's interesting, yes. And indeed, probably because I have so far really touched on the fermionic part of the direction and then defined the double algebra. But then you have to, fermionic parts, you have to.
Yeah, I mean, it has to depend on how you cancel the anomalies. You could cancel the anomalies in some way that doesn't have anything to do with n equals 4.
Mm-hmm. That's right, yeah. So I think the hope is that at least this is a kind of, there is a, Heisenberg, et cetera, it's a kind of most minimal way of canceling the anomaly. So in that case, you might hope of having larger supersymmetry, yes. As you say, in general, we can have anything with a lower supersymmetry. So yeah, probably it's too much to hope for that supersymmetric version of this. But I think it's an interesting question. Yeah, I don't know the final answer.
If you have n equal 8, then you can, if you have n equal 8, then the boundary algebra will have
in the special case, yeah,
a small n equal 4.
Yeah.
But don't n equal 6.
Yeah, interesting. Yeah, I think. Yeah, thank you for asking. I really should look into that. Yeah, I mean, so far we have the very computation, very simple examples, very explicit and in general argument. So, but a lot of examples are yet to be explored. So, I think there's room for further discoveries.
Question in the back.
I just wanted to know if you have any counterexamples to this injectivity.
Surjectivity here.
No, to injectivity, do you have any counterexamples?
For injectivity, not that I know of. At least this one, right? So yeah. Let's see, was that the case? Yeah, I think, yeah, I mean, there is some counterpart of some statement in the Arakawa's paper, but I don't remember if it was this statement. But yeah, I need to check, but I believe that there is no counterexample. I can correct it if yeah. But it's somebody else's paper, so I don't claim to read it too well, but yes. Yes. Ah, this one.
No, not this one, this one.
Oh, horizontal one. Yeah. Oh, sorry, this one, right? So, yeah. When I meant that, yes. When I defined it, yes.
So if there are no more questions, let's thank the speaker. And the next talk is at 2 o'clock.
Just a quick information. Please try to queue. There will be 3 or 4 queues. So 3 or 4 tables. Try to make 3 or 4 queues. Each table will serve the same food. And it will be in the terrace as the coffee break.
algebra and then take conjecture, if you start from here and take the associated variety. Yeah, it's not easy to prove it, as far as I know. So, but we have a conjecture and take the system.
alternates. Date and date. Also, is in the meanwhile.
Go to negative numbers.
I was tempted to do that, but
It's the one when you get to zero and then there's the skull and crossbones.
shut up.
Exactly. No one cares.
Now it is on mute.
Okay, so I'll just. Is that the point of it?
Yes. So there is obviously forward and backward, and so that is the pointer. But you don't. So it's.
There? No. Oh, here.
I mean, you can point it here. Let's see. Yes. But you can also do it there because there is an accelerometer. You know, it should work the same. You can try. Questo è il secondo microfono?
Sì, ma posso usare. Ah, non è carico. Dove è finita la batteria? Finite le batterie. It's slow.
Un accelerometer.
Ok, per oggi va bene.
Ah, ok. Mute, unmute?
No, resta aperto.
Ah, questo resta sempre aperto. Lo posso accendere e spegnere?
Sì. Tasto rosso sotto, premuto 2 secondi.
So you can actually use this if you prefer. I mean, as you either that one.
Does it work?
As you prefer.
Thanks.
Maybe.
Mi dà un attimo. Un attimo. L'ho alzato proprio. Vediamo chi sono io and mechanics 270. Third year. The scale of everything in UK universities
Si accende, bisogna aspettare che ci sia la luce verde.
So the grading, to be fair, is there's no, they work on problem sheets, but it's upgraded.
swing. The pile of exams is big. It took me 3.5 days to. 3.5 days of sort of being in the zone, sort of slightly hallucinogenic, because you get into a zone and you're doing well, and then suddenly you realize, oh my God, I'm not even sure what I'm doing. But it's okay.
One of those exams.
Yeah.
That happened to me last semester. I spent How are you? Nice to see you. Very good. That's okay, man.
See you here? You at CISA?
I'm in CISA.
Okay.
Yes.
Which I just heard is now
On the mountain.
Yeah.
Yes. But we are the institute. Waiting in 2 days searching for them. Which I like it. 2 minutes and I'm holding you up here. Welcome back from lunch. Our next speaker is Jerome Gauntlet, and he'll be telling us about equivariant localization in supergravity.
Can you hear me? Is that working? Is it loud? Okay. Okay, first of all, I'd like to thank the organizers for putting on this wonderful meeting. It's not working? Maybe I'll try a bit higher. Is that any better? No. Can I try this? Is that better? Okay. Is that okay? And that's not okay. 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 Thanks to the organizers, but apologies from the technical staff. Okay, so let me try again. Is this working? Okay. Right. So yeah, thanks to the organizers for putting on this meeting. It's a pleasure to be here. I have a particular connection with ICTP indirectly. Abdusalam, who founded this wonderful, awesome institute, of course, he was also the founder of the theoretical physics group at Imperial College. And Imperial College was his intellectual home while he was doing all these other wonderful things. So he recently had a big celebration at Imperial about 2 or 3 months ago, and we renamed the library in his honor. And we had a big, wonderful outreach day in his honor. Okay, so I want to talk about some work that I have done with James Sparks, my long-term collaborator, and Pietro Benetti Ginellini, who's a postdoc in Geneva. We wrote 4 papers together over the last year, and then there's another paper with James's student Alice Lucia and my student Yusheng Zhao. So I want to talk about equivariant localization. Of course, this is a topic that's known to many of you very well. In physics, it's had a very big impact, starting with the work of Witten, and this highlights Nikita's work on, Nekrasov's work on instanton counting and Seiberg-Witten theory, Peston's work on localizing path integrals, on supersymmetric field theories and curved manifolds, and many, many other things besides. In general, in the physics side, equivariant localization is generally taken as a very powerful tool to simplify path integrals down to some finite dimensional integrals, which one can hopefully then address. What I want to talk about in this talk is something quite different. It's actually quite simple. Could have been discovered 20 years ago, for reasons I'll explain to you later. And it's a tool to compute supersymmetric observables in the context of supergravity, for supergravity solutions, without ever solving the supergravity equations of motion. That's the basic idea. And there's various applications, and the applications I'll be interested in the context of holography, and if I have time, I'll give examples of each of these three. So the first is sort of the most obvious one. ADS-CFT, you're looking for supersymmetric ADS cross M solutions. M is some compact manifold of some dimension. And if you can find such solutions in D equals 10 or 11 dimensional supergravity, you'll have found a dual CFT of one less dimension than capital D. And once you have it, you'd like to compute some observables. If the field theory is of even dimension, for example, the central charge, or the dimension of certain protected operators, and so on. And it's these kinds of observables that one can extract using this equivariant localization. Another application is the program of trying to do microscopic state counting interpretation of black holes in asymptotically ADS. In string theory, one of the big highlights is state counting of asymptotically flat black holes, going back to the work of Vaffer and Strominger. In about 2015, Benini, Hristov, and Zaffaroni started the program of looking or trying to do the same thing in the context of ADS-CFT. So you construct a black hole in an asymptotically ADS space, calculate its entropy, and then try and recover the entropy in the dual conformal field theory that lives at the boundary. So these new tools allow you to get this black hole entropy for black hole solutions without solving the supergravity equations. And then the last topic is when you take a supersymmetric conformal field theory, you put it on some manifold with various other operators turned on, so you still preserve supersymmetry, and then you might be interested in calculating the on-shell action, the supergravity on-shell action, and that, by ADS-CFT, is dual to the partition function of the field theory. And I was just telling you before that localization in the sense of the path integral is used to calculate that on-shell action. And what I'm talking about is complementary there, therefore, in the supergravity side, how you might get this on-shell action and then compare with what you can get from localization in the field theory. So just so we're all on the same page, what do I mean by supergravity equations of motion? So I mean, schematically, I'm only interested in the bosonic fields of the supergravity. So there's some generalized Einstein equations. The Ricci tensor will equal some various stress tensor components, depending on what dimension and what theory you have. There'll also be some additional equations of motion. I'll just generically refer to those as flux equations of motion. So that's the equations of motion. And then ones that are supersymmetric also admit Killing spinners. And structurally, the Killing spinner has this form. There's some covariant derivative acting on the spinner epsilon, and then there's some Clifford connection where you're contracting in the fluxes with the gamma matrices generated as a Clifford algebra in some way. And typically, there's also some other additional algebraic type equations you need to solve. So I'm just being schematic here. I'll give you one detailed example later on if you haven't seen this before. And what I'm interested in is any supersymmetric solutions of any theory that has an R-symmetry Killing vector. So we construct, as a Killing spinner from epsilon, the Killing spinner, we construct this bilinear. So that's a vector field on the manifold. And I want that to be a Killing vector. I demand that's a Killing vector. And I also want the Lie derivative of the spinner with respect to the Killing veil to be charged. So Q is some non-zero parameter which carries the charge of the Killing spinner. So this is extremely general. It's not completely general. For example, if you take a Calabi-Yau manifold, they have covariantly constant spinors, but they have no killing vectors. But that aside, this is a very, very general setting, and I'll give you several examples where this structure exists. So as soon as you make that observation, there's a very simple thing you can think about, is you can construct the equivariant exterior derivative, which is just a combination of the ordinary exterior derivative plus the contraction with the killing vector. And if you square that operator, it squares to the Lie derivative. So if you're acting on the space of invariant forms on the manifold, then you have an operator which squares to 0. So there's a corresponding cohomology. So a very obvious question in supergravity, therefore, is what is this cohomology telling us? And it's surprising that this hasn't been asked, as I said, many, many years ago. There's more general spinor bilinears you can construct. And schematically, here they are. So here is some rank R form. So gamma R is just some anti-symmetrized product of the gamma matrices generating the Clifford algebra. And these are just some local coordinates on the manifold. And there's, again, depending on the dimension you're looking at, there could also be the charge conjugate spinors that you can construct some differential forms from as well. So you can construct all of those differential forms as spinor bilinears. And then a program that I and collaborators initiated about 20 years ago was to recast the information in the killing spinor in terms of a G structure, which is essentially algebraic and differential relations captured by these killing spinor bilinears. So there's a lot more to say there, but this is work from a long time ago, and I don't want to go through that. But that was a big program that led to a lot of successes of understanding generic classes of supersymmetric solutions of supergravity theories. The new observation is this. This is the main point. It's very simple, but and is that you can construct a multiform. So it's a linear combination of differential forms of different rank, which are polynomials in the supergravity fields and the bilinears, which I just mentioned, and they're equivariantly closed. So there are these natural canonical equivariantly closed forms. And just again, if you haven't seen this, for this to be 0, this has to be a polyform, because remember, D increases the rank, so the D of this form should equal the contraction of this form with the killing vector. And there's a sequence of relations to make that equivariantly closed. So that's a new observation. In general, there are these equivariantly closed forms in supergravity theories. What are they good for? So a number of comments. The first is, and this will be important later, is to construct these forms, you only need a subset of information in the killing spinor equations. You don't need all of the information in the killing spinor equations and the equations of motion, just a subset. So correspondingly, when I said that these equivariantly closed forms, it's an off-shell statement. And that off-shellness will come back a little bit later. A second point is that there's several of these equivariantly closed forms in a given theory. We don't have, at the moment, any canonical general understanding of where they're coming from. It's just take a supergravity theory, start playing around this, you can just start constructing them. So that's an open question, what the bigger, deeper reason for all this is. But nevertheless, in any given context, several of them exist. And most importantly, and probably quite closely related, is you can use these to actually obtain physical observables of the theory just using this equivariant cohomology. In other words, the topology of the solution and the R-symmetry being the killing vector, that's enough information to extract out this physical information, provided that is, the solution exists. So if a supergravity solution exists, this technology allows you to extract out the physical information. And the key tool to extract out the information is this famous BVAB theorem. So let me just run through this. I know many of you would have seen this, but if you haven't seen it, it's worth running through. So I'm taking the M to be an even dimensional manifold, but I'm going to think about here integrating an equivariantly closed form phi over the manifold, or an invariant closed submanifold, invariant under the action of the Killing vector. And when we have an integral of a polyform, it just means integrate the rank form, which is the same rank as the dimension of the space you're integrating over. And what this theorem says is that the integral of this equivariantly closed form is given by a sum of integrals over the fixed point set of the action of the Killing vector. So the fixed point set of the Killing vector is where the Killing vector vanishes, so where psi equals 0, and that could have various disconnected components of different dimension. So here I've got the sum over the different fixed point sets, different codimension, and then I've got an integral here over f, and f star is the pullback of the fixed point set to the manifold. That's the same equivariantly closed form that appears here, is appearing here. Bi, that's appearing here, are the weights of the action of the Killing vector. So if you take the fixed point set, there's some normal bundle, the directions away from the fixed point set, and I'm assuming just for simplicity that there are some of line bundles. So just think of these as a sum of complex lines. And the Killing vector in some local coordinates can take that form. So take your normal directions, think of them as a bunch of R2s, and you're just rotating in ordinary polar coordinates around the origin of each of those points, and the weights of each of those terms is just the weights of the action on that normal bundle. So you can see the BIs appear here, and they also appear here, and finally what's this C1 here? That's just the Chern class of these line bundles. And it's okay, we're integrating differential forms, so as usual, you just expand that, bring that up to the numerator, and then you integrate the corresponding rank form. And then finally, we also allow here, this D here, is that the normal space, I said it was a bunch of complex lines, but you can actually allow that to be orbifolds. So there's, gamma is a finite group of order df, and then df then pops up in this term here. So this formula is basically once you have some equivariantly closed forms, you want to use this formula as much as you can. It starts with a bigger integral and reduces it to smaller and smaller integrals. I'm just going to rewrite that here because it's even simpler if I do it this way. So I've just expanded that Chern class term in the denominator and collected the terms. So here's the integral of phi on the left-hand side, and the fixed point contributions is just this simple thing here. So there's n weights, because there's 2n normal directions, and phi naught is just the lowest component of the equivariantly closed form. So if you just have fixed points, your integral is just given by evaluating these, that term at each of the individual fixed points. If you have fixed two-dimensional surfaces, you now have to do this integral, and you can see you have a combination of phi 2 and phi naught with the Chern classes of the line bundles. Good, so that's the BVAB formula, which is what we use, and I'm not going to go through many details when I eventually come to the examples, but this is the key tool where one does all the integrals that one wants to do. So just finally, just to give then a trivial example, if we just take the two-sphere, here's the metric on the two-sphere in some standard coordinates, and I take psi to be just the Killing vector which rotates the two-sphere. Clearly that has two fixed points. You can do this in your head. Here is an equivariantly closed form. It satisfies this condition here. So the BVAV formula says that if you want to calculate the volume of the two-sphere, you can integrate phi along the two-sphere. That has two fixed points, so you should evaluate phi naught divided by the weights at the north and south pole. And then if we just look at this, if we go to the north pole, we see that B is 1, because just d by d phi is rotating the tangent plane by weight 1. If we go to the south pole, B is -1, because there's an orientation, it's rotating in the opposite direction. So you simply just substitute into this formula, and hey presto, 4 pi appears. So of course, that's a trivial example because we know how to calculate the volume of that two-sphere, but of course, this formalism can be used in highly non-trivial, non-obvious situations. Good. Okay, so with those preliminaries out of the way, I want to now just, as I said, hopefully talk about 3 examples, if I have time, and we'll see how far we get. So there are going to be 3 separate examples of supergravity solutions where we'll construct some BPS observables without solving the PDEs. So the first class is the general class of ADS5 cross M6 solutions of D equals 11 supergravity that preserves supersymmetry. So these are the most general ways in which you could have an n equals 1 supersymmetric conformal field theory realized with an 11-dimensional M-theory dual. And the data, or here is the metric, ADS5, here's M6, and lambda is a function on M6. So this has all the isometries of ADS5, this warped product metric, and G4, the other bosonic field of D equals 11 supergravity, is a 4-form on M6. And actually, we need a flux quantization condition on that, so there's some normalization constant, but G4 is an integral cohomological class. We want this to be supersymmetric, so we want the solution to admit solutions to the 11-dimensional killing spinor equation, which I'm not going to write down, but the 11-dimensional spinor I decompose into a 5-dimensional spinor, a killing spinor on ADS5, and epsilon is a spinor on M6. And if you look at that in detail, that 11-dimensional supersymmetry condition, the one we're interested in, translates into this condition in 6 dimensions. So there's a covariant derivative acting on epsilon, gamma star is a chirality operator, and here's the 4-form flux contracted in with the gammas generating the Clifford algebra, and there's this algebraic condition down here with some slightly different factors, and so on. Okay, so if you're looking for supersymmetric solutions of this form, you want to solve the equations of motion, which I haven't written down, for this ansatz, and ask that it also admits solutions to these killing spinor equations. So the program is construct bilinears with some good taste and see where it takes you. And you construct a scalar. It turns out that the scalar is, the derivative of the scalar is constant, so we'll normalize that to 1. You can construct another scalar on M6 using the chirality operator as a bilinear. You can construct a 1-form K and a 1-form xi flat. You can construct a 2-form Y and a 2-form Y primed with gamma star. That's the key things we'll need. Not obvious that that's the case, but it is. First of all, xi is the 1 form that's dual to the R-symmetry killing vector. Now, the fact that we have an R-symmetry killing vector is absolutely expected because any n equals 1 conformal field theory has an R-symmetry that must have been realized by a killing symmetry on M6. And we knew it was there, and there it is. Second comment is we can certainly construct more bilinears. We could construct 3-form bilinears, 4-form bilinears, which then would get, by Hodge duality, be related to 2 forms. But we could also construct bilinears using the conjugate spinor. And the point here is that we won't need them for what I want to do here. In the old work I did 20 years ago, we used everything, and we came to some nice conclusions, which I don't want to go into that. The main point here is you can get a lot out with a lot less. And as I said before, this means that we're only using a subset of the killing spinor equations and equations of motion. So what I'm talking about is going to be partially off-shell. Convenient definition, instead of using sine xi as eta, I'll just dress that with the warp factor and call that y, and that's the same information as the bilinear, and it turns out dy is related to the 1-form k. And here is the equivariant, one equivariant in the closed form. It's the volume on the 6 manifold, star of y, that's a 4-form, y is a 2-form, and it's dressed with the warp factor and this spinor bilinear here, and then y cubed appears there. It's not at all obvious this is equivariantly closed, but go back to those killing spinor equations, and you just work hard to do that, and it is. And what's nice is that the top form is not any old form. If you integrate phi along the whole manifold, it gives you the acentral charge of the dual field theory. So in other words, if you want to calculate the acentral charge of any solution of this form in M theory, you can just evaluate that integral, and you can evaluate it using BVAB. Second, there's another one, which is an equivariant completion of the 4-form. So there's a 4-form flux, there's a 2-form, and there's a scalar. And this is also equivariantly closed. So I told you that we want to impose flux quantization as part of the physical criteria of solutions. That can also be implemented using BVAB. Why? There's why. Okay. Good. Okay, so now we've got those equivariantly closed forms. I want to now put these tools to work and show you that it's useful. And an alternative title would be computing the acentral charge without trying. I mean, trying is construct a supergravity solution, solve all the PDEs or the ODEs, then do the integral and see what answer you get. And we're going to get it much more simply than this. So I'll illustrate using a particular class of examples. And this is just illustration. There's other things you can do, but I think these are the simplest ones to explain the formalism. So I'm going to consider taking 5 branes and then wrapping it on the Riemann surface inside a Calabi-Yau threefold. So this is an old story that was first introduced into our field by Maldacena and Nunes, who considered taking 5 branes and wrapping them on a Riemann surface of genus G. This, and more recently, we realized that you can also generalize this to wrap 5 branes on spindles. A spindle is an orbifold. It's topologically a 2-sphere, but at each of the poles, it has orbifold singularities labeled by 2 integers. So there's no covering space which gets rid of those orbifold singularities. And in studying both these examples, they have some different features, and that's why I want to discuss both of them. So a local model of the Calabi-Yau would be you take your Riemann surface and consider the sum of 2 line bundles over the Riemann surface, and to make sure the first Chohan class vanishes, you should have this condition here. P1 plus P2 is the Euler character of either the spindle or the Riemann surface. That's the topological part of the topological information we're going to put in to extracting the answers for the supergravity solutions. So you take your 5 branes, you wrap them on this Riemann surface. You have 4 dimensions of the 5 brane which are non-compact. If at low energies this flows to a conformal field theory, there should be an ADS 5 cross M6 solution. You're not guaranteed that, but if it does, then there should be such a solution. And moreover, the solution should have this topology. A 4-sphere bundle that's fibered over the 2-dimensional surface. And if you think of the 4-sphere as embedded in R5, like this, then the 2 factors of C1 are twisted using those line bundles I just mentioned before. Okay, so what I'm saying is, think about 5 branes wrapping Riemann surface in Calabi-Yau. That's telling you a lot about the topology of M6 that in the ADS 5 cross M6 solution. So I'm using that information. So let's do the Riemann surface case and then look at the spindle case. So the Riemann surface case, we're almost done, in fact, although I'm not going to show you all the details. If I think of d by d phi I as rotating these 2 complex lines I mentioned up here, they will give rise to Killing vectors that are acting on the 4-sphere. And that, much like the 2-sphere example in that little simple example I gave you before, these Killing vectors will have fixed points at the north and south pole. So this Killing vector, this R-symmetry Killing vector, will have fixed points at the north and south pole, and those fixed point sets are the Riemann surface itself. The 4-sphere is fibered over the Riemann surface, so if you go to fixed points at the north and south pole, you have a copy of the Riemann surface. A detail is that if you look at the spinors at the fixed point sets, they're necessarily chiral, and that translates into this one extra condition. There's a little bit of work required to get that, but that's a fact. And at this point now, we have our equivariantly closed forms. I've told you about the topology. There's fixed points. We just go to BVAB and do the integrals. And they're not that hard, but I'm not going to do any more details of that. I'm going to just tell you the answer. And the answer is this. So we implement flux quantization. So the integral of G4 on the force sphere, that's the only force cycle that's around, is n. And the central charge takes this very simple form here. So P1 and P2, that's the topological information telling you about the Calabi-Yau your Riemann surface is sitting in. And B1 and B2 are the two weights of the killing vector that we inputted in. I didn't, that's a standard thing of ADS-CFT in the sense that that top form back here, if you integrate this, just forget everything else, but you just integrate that, that will give you your 5-dimensional Newton's constant. And the 5-dimensional Newton's constant is known to be proportional to the acentral charge of the field theory. Yeah, thanks. That's a standard ADS-CFT fact. But of course, what we're doing just to, is using the lower dimensional forms to do that integral. And in fact, yeah, it's fixed. There's a fixed Riemann surface, so that Y integral comes into play. I don't want to go into the details of the computation. The spirit of it is BVAB just says your higher dimensional integral turns into simpler, smaller ones. And moreover, when you go through it, you get right down to this very, very simple answer. Now, the first thing about this, and I told you this several times already, this is an off-shell result. This expression is not the final on-shell result. It's subject to this constraint, which I said came from chirality conditions. But what you should do is extremize this over B1 and B2 subject to that condition. And if you do that, you'll get an answer which is exactly the same as the known supergravity solution answer. But we never solved any PDEs. All I just assumed is that the solution exists, inputted the topology. This result also agrees with the off-shell field theory computation. So you can take the M5 brane, you can look at its anomaly polynomial, reduce on the Riemann surface to a 4-dimensional theory, and then there's this technology of A extremization, A maximization. And A maximization is a procedure to maximize the acentral charge as a function of trial R-symmetry charges. And that's exactly what's happening here on the gravity side. It's exactly mirroring those results in the field theory. And I can't emphasize enough that this computation I've just outlined is much simpler than constructing the supergravity solution. Okay, so that's the Riemann surface case. What about the spindle? It's almost the same, but there's one interesting feature which is different, which is a spindle. I didn't tell you this before, but I demand that it has a killing symmetry rotating the spindle. That's my definition of a spindle. So the killing vector could be the same one I was talking about before acting on the force sphere, but it could also have a leg rotating the spindle. And if you think about that for a moment now, the fixed point set is at the north and south pole of the force sphere plus the north and the south pole of the spindle. So you do the same thing with BVAB, but now there's just fixed points. So it's a different computation, but you go through the technology and you come up with this answer here. So B1 and B2 are the weights at the north pole of the force sphere and the north pole of the spindle, dressed with some extra factors. B0 is the factor of the leg of the killing vector along the spindle direction, and B1 plus B plus 2, B1 plus or minus, B2 plus or minus, are constrained by these conditions here. The details don't really matter. It's the spirit of the fact that you get the result and you get an answer which now requires you it's an off-shell answer, extremizing not just over B1 and B2, but also B0. And again, you get the exact result that you get from the explicit supergravity solution. It also agrees with the off-shell field theory computation, which you can get by anomaly polynomial computations. And for people in the audience who know about this, the notion of gravitational block was introduced by Hosseini, Hristov, and Zaffaroni. That was like a field theory way of getting expressions for central charges, and you can see this is breaking up into two pieces, one located at each pole, and they called this a gravitational block. So in a sense, what I've just told you is from a gravitational point of view, we've proved the gravitational block formula in this context. But that's an aside.
When you're varying the B's, when you're extremizing with respect to the B's, you're varying the geometry or the killing form or both?
No, it's the killing vector. So
You've got a fixed geometry and you're varying the killing vector.
Fixed topology.
Yeah.
And then I have a killing vector.
I see. You have a vector space of killing vectors and you're varying within that vector space.
Exactly.
I see.
Exactly. Okay, so that's the end of example 1. I'm hopeful we're probably on track to do all 3 examples. Example 2 has a slightly different flavor. So it's to do with computing black hole entropy for ADS4 black holes. So we take a 4-dimensional gauge supergravity with an ADS4 vacua, and we imagine that inside that ADS4 space, there's a black hole. And if it's supersymmetric, as you go to the near horizon, it will look like ADS2 cross M2. M2 is the horizon of the black hole, and we want to calculate the Bekenstein-Hawking entropy of that black hole. So the topology of that horizon could either be a Riemann surface, or it could be a spindle. Again, this is sort of an older story, this is a newer story, and you might wonder what sort of black holes we're talking about with spindles. And the spindle, the orbifold singularities of the north and south pole, are associated with the black hole accelerating, or there is acceleration in the black hole geometry. In any case, we want to calculate the area of this at M2. And we can again do this by localization. And it's effectively a new version of the attractor mechanism in the context of gauge supergravity black holes. So just a quick summary of the ingredients that go into n equals 2 gauge supergravity. So we have, I'm imagining we've got gauge supergravity coupled to n vector multiplets. So we have the bosonic fields are a metric in this 4-dimensional theory. There's n+1 gauge fields labeled by index capital I. There's n complex scalar fields labeled by x capital I as a function of the zi's. So there's a constraint amongst these. And those zi's parameterize a special Kähler manifold, which has a Kähler potential K. There's a holomorphic prepotential, which is a function f, which is a holomorphic function of these xi's. And I said it's a gauge supergravity, and the gauging is specified by these fi gauge parameters. If you've seen this, you know this very well. If you haven't seen this, this is just some ingredients that go into defining the theory. So starting with these ingredients and the killing spinor equations, which I'm not going to write down for this case, you start playing around. Can you construct some bilinears? Can you construct some equivariantly closed forms? And you can, and the answer is you can. So you can then start evaluating things using BVAB again. And I'll focus on this spindle case. And the reason why, if you're fully up to speed with me at the moment, is this, for gene is bigger than 1, there's no killing vectors on this space. So I need a killing vector to play my game. So this spindle is the context in which we want to use this technology. The two-sphere case and the torus are special cases. But generically, it's the spindle case you can use this technology. So as I said, I'm not going to tell you anything about what the equivariantly closed forms are, how you actually do the computations, but you can do it. They're not that hard. And the final result for the black hole entropy is given by a sum of 2 terms, one associated with the north pole of the spindle, another one with the south pole of the spindle. And the holomorphic prepotential is appearing here. And it's a function of what I've called dress scalars. So if we look at this for a second, x capital A were the scalars of the gauge supergravity, k is the Kähler potential, lambda is a warp factor, and p is a spinor bilinear, which I didn't define for you, but that's what it is. So you consider this specific combination together to form little xi, and then you evaluate the prepotential as a function of those x's at the North Pole and the South Pole. And B naught is the component of the, it's the weight of the killing vector along the spindle directions. And there's some constraints on these x plus and minuses. And again, the details don't matter, but you can see the gauging parameters for the x pluses satisfy this condition. On the x minus, there's a slightly different condition. There's a constraint on the magnetic fluxes, which is related to x plus and minus. But the most important thing is all this data, what's free here is B naught and x plus or minus. That's what's appearing as free data here. So I'll come back to sigma in a second. B naught, x plus or minus is the data here. These constraints say that if you extremize over B naught, x plus or minus, it's actually a closed system and you can solve it. So you do that extremization and you get the entropy of the black hole. Not in detail. In general, there's eye extremization that people have thought about in the context of these black holes in ADS. So that's the spirit of where it comes from. But the map between the extremization I'm talking about and what's happening in field theory, there's no direct map between those. But overwhelmingly, it feels like there should be. Yeah, the sigma, it's a technical point, but it turns out that on spindles, there's two ways to preserve supersymmetry, are called a twist or an anti-twist. And a twist means that the spinor chirality at the North Pole is the same as at South Pole. Anti-twist, they're opposite chirality. In any case, there's two cases to consider. But both those cases can be implemented here. You can extremize over this, and you get the known supergravity result in the known supergravity solutions. And again, we didn't solve any equations of motion of the supergravity. We just used equivariant localization. Three quick comments that are a little bit aside, but let me just quickly run through those, and I'll turn to the last example. I've been just talking about the spindle now, but if you just formally set m plus minus to 1, and you take B naught goes to 0, that's the weight along the spindle direction, you actually get the result for the black hole entropy of spherically symmetric black holes in gauge supergravity. And you, in fact, recover this old attractor result of Cacciatore and Clem, Dallegata and Necchi. Another comment is, I was talking about general gauge supergravities, but if you take the STU model, which is a specific one, you can uplift the solutions on the 7th sphere. And if you do that, you'll get an ADS2 cross Y9 solution, and Y9 is an S5, S7 fibered over spindle. And that Y9 has what's called a GK geometry, and with a completely complementary set of geometric techniques, Martelli, Sparks, and collaborators and I have been exploring that. And that's sort of a complementary set of results where you can get the answer I just gave up using a completely different set of techniques based on this 9-dimensional geometry. So it's an advert for this work, not directly connected. I was talking about vector multiplets. You can also add hypermultiplets to this story, but I won't say anything more about that now. And the final example is, it's again in D equals 4 gauge supergravity, n equals 2. I'll be thinking about Euclidean gauge supergravity now. And this is so simple, I can just write down in the minimal case what the full theory is. So it's just Einstein-Maxwell with a negative cosmological constant. There's a boundary action, which is given by extrinsic curvature term, a constant term, and a Ricci scalar of the boundary. The killing spinor equation is also simple enough. You can just write it down. There it is. And the significance of these solutions, in general, is that any solution of this theory, you can uplift on a 7-dimensional Sasaki-Einstein manifold, and you'll get an 11-dimensional solution that's dual to a 3-dimensional n equals 2 SCFT on the boundary of this manifold M. So I'm now thinking about the full 4-dimensional manifold with a boundary, and that's where this 3-dimensional field theory lives. So if you can construct such a solution, you say, I'm interested in a particular conformal field theory on a particular 3-manifold. You would like to solve the equations of motion where you fill in that 4-manifold with a 3-manifold boundary, calculate its on-shell action, and that should give you the logarithm of the partition function of the dual field theory. This can be constructed using localization in favorable situations. And here we want to say, what can we say about that using localization in gravity? There's one subtlety, which is you can't use BVAB directly because we now have a boundary, and BVAB is not set up, it's based on closed manifolds. However, that turns out not to be an obstacle. So the on-shell action turns out to be the integral of an equivariantly closed form, which I'm not going to write down, but you construct it from bilinears, much as I was indicating before. But you still have this boundary action. But we can't just use BVAB directly on this. But if you look at the proof of BVAB, it's basically Stokes' theorem. So if we assume that the fixed points are only in the interior, in the bulk of the four-dimensional geometry, this integral is a boundary integral plus a fixed point integral. The fixed point integral is BVAB, and the boundary integral is something you have to deal with. And interestingly, that boundary integral exactly cancels this one. So after all, the BVAB formula of just evaluating the fixed point set does work. What's the result? Well, here we have a four-dimensional manifold. Killing vectors, the fixed point set's either two-dimensional or four-dimensional. So Gibbons and Hawking in 1977 called these nuts and bolts. Nuts are fixed points, and bolts are fixed surfaces. And I think I was mentioning this before, the spinor has fixed chirality on the fixed point set. So the final answer is this very nice formula here. So you do the equivariant localization, use BVAB, and you get a sum over nuts with particular chirality labeled by by plus or minus. You have this nut contribution, which is just the weights of the killing vector, a function of those. And then there's also these integrals over the fixed bolts. And we have the Chern class of the tangent bundle, and we have the Chern class of the normal bundle, and that's the final answer. So no matter how complicated your solution is, how many bolts and nuts it'll have, then this will be the answer. One thing I want to emphasize, which maybe in the examples I said before, I illustrated with known supergravity solutions. So I said, here is this new formalism. You go through it and you get an answer, and oh, look, it agrees with the known one. But that's not the point, of course. The point of this whole formalism is it's going to give you tools to get the answer when you can never construct the solution, or it's extremely difficult. And this is one example. So provided the solution exists, this will be the answer. And there'll be many cases where, you'd have to solve a couple set of PDEs to find these solutions. I'll just quickly flash up as I'm running out of time. Still in the four-dimensional theory, I was just talking about minimal gauge supergravity. You can add in vector multiplets, and the analog of that formula I just wrote down just gets dressed like this. So here's the on-shell action. It's a sum over nuts as the weights of the killing action. But now the pre-potential is appearing here as a function of these dress scalars u. And there's an integral over bolts with some derivatives of the pre-potential and so on. And this result basically covers the case of STU. It's the dual supergravity results for ABGM and S3, ABGM and S1 cross Riemann surface, ABGM and M3, where M3 is an S1 bundle over a Riemann surface. And these cases, the gravity solutions are known, partially known, and in this case, basically not known. Whereas this answer, using these much more general techniques, is just giving it to you straight away. Okay, so that's pretty much all I wanted to say. So just to summarize, the main take-home message is it's a new technique for computing BPS observables for supersymmetric solutions in supergravity. It's very, very general. You can just take any supergravity theory you like, and you're going to find something like this. I illustrated with a bunch of different examples. You can certainly recover, as I was just saying, known solutions, but the main interest in this is that it's going to give you answers for solutions that probably can't be constructed. What I mean by probably can't be is it'll be solving a system of PDEs in at least 2, if not 3 variables, and even maybe numerically it'll be even out of reach. We've looked at a few other cases. And I'll just quickly flash what they are. ADS 3 cross M8, corresponding to 5 branes wrapping 4 surfaces, holomorphic 4 surfaces. ADS 3 cross M2, and 6-dimensional Euclidean supergravity. But there's many, many more cases to look at. So there's an invitation to young people to work on this topic. There's lots to do. One thing, all these examples, M8, M2, M4, and so on, they're all even dimensions. And that's where BVAB naturally works. But odd dimensions, there's many interesting supergravity questions in odd dimensions. I think something can be done, but nothing's been done on that yet. At the moment, it works, but we don't quite know why it works. At this stage, the way I would say it works is take any supergravity, think of the kind of solutions you're interested in, think of the observables that you want to calculate, and then go and try and construct a equivariantly closed form for it. And in every case, that just works. So it's not, I mean, you have to play around, a bit of work's required to find it, but in every case, that's worked. And the last comment I wanted to make was, this is not completely magic. You have to know the solution exists. That once the solution is known to exist, then this technique will then give you the answer to these physical observables that I was mentioning, different in each cases. I do wonder if there's a converse to this, that in some cases there's sufficient conditions which you can at least conjecture where existence would be guaranteed. So for example, for the ADS5 cross M6 solutions, say you input a topology, you say here is the action of, here is the choice of killing vector, some extra information, you go through the formalism, you calculate a central charge. If the central charge is negative, there can't possibly be a solution. You can actually calculate some more things, which I haven't had time to tell you. For example, the conformal dimensions of some chiral primaries. So it could be, do the BVAB formalism calculation. If the central charge is positive, if the dimensions of these conformal primaries are all satisfying unitary bounds and so on, then there's a converse and the solution must exist. But that's pure conjecture. But that, at least in some of these cases, would be a very nice thing. I'll stop there.
I was wondering if you have any comment on possible interplay between these and twisted supergravity sort of calculations or ideas. Like, I don't know if when you localize to something which is not a point, but maybe is a higher dimensional manifold, could it be like a variational version of this extremization over B's that you had? Something where you extremize over functions or lower dimensional fields?
So, yeah, I mean, the short answer is I don't know, but in this context, there are cases where the fixed point set is not just points, it's high dimensions, but the final localization that you need to, sorry, the extremization you need to do is just over the choice of the killing vector. Yeah, so in that sense, the extremization, I mean, the extremization that happens in this formalism is sort of the one you would expect from the field theory point of view. And that's just a straightforward choice of the R symmetry. However, there could be more that's there. I think the biggest thing I'd like to know if there's any direct connection between this and localization of the path integral. I mean, there's some algebraic structure in both cases. That's just somehow the essence of it. And we haven't got that understanding on this side. But there's just some algebraic little module that's there that's just being cranked along, I think. Some informal sense.
I had a question here. I was wondering, in this calculation where you had a cancellation between a term coming from the bulk and the boundary action, I was wondering, in order to check this cancellation, does it work like specifying a particular supersymmetric boundary condition, or you can check it irrespectively of the boundary condition?
Yeah, so you need to have the renormalization scheme, which is those particular counter terms, that is supersymmetric. So so for the minimal gauge supergravity, it's kind of straightforward, but for when you add in vector multiplets, you have to have all the right superpotential terms and so on. So you have to have a supersymmetric scheme.
Okay, thanks.
So if I understood correctly, you were saying that there's some integral you begin life wanting to compute on supergravity side, which has some known meaning on the other side, and you have killing vector on supergravity side, or you look for one which has some known meaning on the other side, this R symmetry or whatever. So, and then you do some procedure, some new procedure on supergravity side, which is taking equivariant completion, which doesn't change the integral over there. And so what I wanted to know was, is there some analog, what sits on the other side from taking this operation of taking equivariant completion? Does that question make sense?
Yeah, I don't know the answer to it, if it does make sense. Yeah, I mean, to my mind, at the moment, it still seems somewhat miraculous. In fact, historically, the reason, I sort of rushed over that, but this formula here, these people constructed this formula just by brute force. So in a sense, I think another way of saying it is this equivariance completion and the story and so on is an explanation of where that came from. But if there's more physical interpretation of these lower dimensional terms, I mean, there are bilinears in the killing spinner, but that's not a direct physical, kind of identified as a direct physical observable. It's somewhat miraculous, I still think.
Maybe, so is what you're saying that an answer to my question would have to explain this formula on the others, on this field theory side?
No.
Without doing hard work?
Well, it depends, I suppose, from a field theory point of view. If someone told you, I can calculate this from some field theory technique, and here is a nice, beautiful formula, because ADS-CFT works, you might feel, I must be able to calculate that from supergravity. And up until now, the other way, well, yes, I'll go and construct a solution, and I'll just solve PDEs, and I'll do everything, and I get the answer. But what I'm saying is, no, you don't. There's a much simpler set of tools to see why to obtain that calculation. But exactly what that correspondence is, I don't see at the moment.
So there is some discussion on when you have the toric Sasaki-Einstein, people discuss the extremization, and then in that case, the vanishing has a meaning in terms of the eliminating the Futaki obstruction, so obstruction to the existence of metrics. So I wonder if your quantity can be related to some obstruction to the metric, so that you're raising the question of existence, but I wonder it is automatically guarantees the vanishing result.
That was the kind of, so as you know, if those toric Sasaki-Einstein, there was the possibility of obstruction, then people proved, in fact, they weren't obstructed.
Yes.
So that comment I made right at the end about the, well, it's a bit vague, but this last point, this acentral charge and the conformal scaling dimension of these chiroprimaries would be something like vanishing a Futaki event or something.
I see. It'd be nice to make it refresh.
It's a very physical thing, which would be very natural.
Interesting, thank you.
Yeah, thank you. Could you say a bit more what goes wrong in odd dimensions with this BVAB theorem? Is it something very deep, or is it just...
There's some version of the BVAB theorem in odd dimensions, but you have to effectively take another vector and effectively do a Kaluza-Klein reduction with respect to that vector, and then show that your final answer didn't depend on the choice of vector. It's a very clunky proof. So there's something known, but it's a bit, I don't know if this is the best one can do, but it's something along those lines one would have to do. So I think it's definitely something to be explored.
Okay, thank you.
Are there any more questions? In that case, let's thank Jerome again. speaker, Ilya Arjut, will be here in 2 minutes.
Oh, it's out of battery. And otherwise there is always this, there is also this one, which is one. Oh, it's off.
Battery low.
Yes, there is another one. Can you, this one doesn't even turn on. So. Hello. Yes. The center, more or less.
Okay. Is this okay? I can carry this in my hand.
And
Oh, Julia Argus, that's correct. Nice to meet you too, thank you.
I flash these signs when 20 minutes and so on.
Okay, that sounds perfect. Thank you.
there is also the clock over there.
Okay.
Over there.
Perfect.
So this one, so the forward, backward, and with this one it's an electronic pointer.
Ah, nice.
You can point here, you can point there, wherever you want it works.
Ah, perfect. That's very nice. Thank you very much. Let me try if it works. Okay. Everywhere it works.
Try the pointer if you want.
Yeah. Okay. Okay, this looks great. This looks all good. Let me go through the end. Perfect. Thank you very much.
Shall we start?
I'm ready.
Our next speaker is Julia Argus, and she'll be telling us about KSGA moduli spaces of low-collabial surfaces.
Okay, thank you very much, and thanks to the organizers for having me speak here today. I'm more on the mathematics side, so my talk will be more on the algebraic geometry side. I think it actually is turned on. Can you hear me? That's fine, okay. Okay, yeah, I can also try to stay closer to here. Thank you. So I will essentially tell you about some classical topic in algebraic geometry on understanding the geometry of particular types of moduli spaces, of surfaces. And while the problem to understand the geometry of such spaces a priori has nothing to do in its formulation about mirror symmetry, the way we solved this problem actually goes through mirror symmetry of three-folds, and I will tell you how this works. So to solve this problem in algebraic geometry, we developed a framework mathematically to understand mirror symmetry for non-toric, non-compact Calabi-Yau three-folds. And this is what we did in our recent paper together with Valery Alexiev and Pierrick Bousseau, which you can find on arXiv. We finished a couple of months ago. And as we did this, we noticed that the mirror symmetry framework we developed to solve this question in algebraic geometry actually enables us to solve another open question in physics, which is related to 5D superconformal field theories. And this is what we are currently writing up with in work with Pirik, and this will be the topic of the talk of Pirik tomorrow. So I will just tell you what question is related to about this physics side briefly, and Pirik will talk more about that. So here's the plan of my talk. I will tell you what are the KSP modular spaces of Kolar, Shepard, Byrne, and Alexiev. In the toric setup, I will review the known results of modular spaces of such toric surfaces, and I will explain it by using mirror symmetry, how these can be understood by looking at toric mirror symmetry for Calabi-Yau threefolds. And then I will tell you what are KSP modular spaces in the non-toric setup, modular spaces of so-called log Calabi-Yau surfaces. And I will tell you how we mathematically understand mirror symmetry for in the non-toric setup and how we use it to understand these spaces. So the main result of the talk is going to be the KSP modular spaces of these non-toric so-called log Calabi-Yau surfaces is going to be up to a finite cover, a toric variety. And at the very end, I will elaborate how this is related to 5D superconformal field theories. Okay, to start with modular spaces, so one of the most extensively studied modular spaces in algebraic geometry is known as the Deligne-Mumford modular space of stable curves, M bar Gn. So it's this space, it's the base where every point corresponds to a stable curve, which is the data of a reduced curve of arithmetic genus G, which has at first nodal singularities, together with a bunch of points on it, P1 to Pn, which you can use to impose a stability condition, which requires the automorphism group of this curve together with these points to be finite. Mathematically, this is equivalent to saying that the canonical divisor given by the sum of the canonical divisor together with these points should be ample. And this modular space is extensively studied. It's a nice mathematical space. Deligne-Mumford showed that it's a DM stack of dimension 3G minus 3 plus n. And over the last 30 years, Kolar, Shepard, Byrne, and Alexiev developed a theory to study generalizations of these modular spaces parameterizing not curves, but higher dimensional algebraic varieties. So there are spaces like this, MKSB, the KSB modular space, also known as the KSB modular space of stable pairs. Its points correspond to pairs YB, where Y is any projective variety of any dimension, and B is the divisor in Y. Analogously to curves, you want this pair to have particular types of singularities, which we call semi-log canonical singularities, coming from extensively studied in the context of minimal model program in maths. So you can think of these as higher dimensional analogs of nodal singularities. And again, there's a stability condition analogously requiring the sum of the canonical divisor and B to be Q-Cartier and ample. So this is a space to have a picture whose points correspond to such varieties together with some divisors in them. Due to the fact that, though, as you can see, SLC singularities are significantly more complicated than nodes. In particular, the deformation theory of a node is a lot easier than the deformation theory of the singularities. Due to this fact, we actually have the issue that the connected components of the modular space here, while it is a Deligne-Mumford stack, unlike in the previous case, it's not generally irreducible. So for people working in this area, the general goal is to describe particularly reducible components of this modular space and to tell what is the geometry of irreducible components. I will do this in the toric setup. I will tell you this first in the toric setup. If you look at toric varieties, what is the geometry? So to do this, I want to first review a few facts about toric varieties. So these are varieties you can obtain purely combinatorially. If you start with a lattice polytope P in Rn, you can naturally associate it a polarized projective toric variety, Y, which is the approach of a monoid algebra, where you obtain by Cp, I denote the monoids of integral points in the cone over B. And there's a natural toric boundary divisor, which is the anti-canonical divisor given by the union of torus fixed divisors, which I denote by D. And also associated to this lattice polytope, there is an ample line bundle which defines you the polarization, so that the sections of this ample line bundle admit a nice toric monomial basis, which are indexed, which I denote by Z to P, the basis elements, which are indexed by integral points in the lattice polytope P. So here's an example of P2. So associated to this triangle is a lattice polytope with its anti-canonical polarization R3. If you chop off a triangle of normalized area 1, it amounts to doing a blow-up of P2, doing a toric blow-up. If you chop off 5 small triangles, you will obtain this pink lattice polytope. I will keep as a running example, which amounts to blowing up P2 at 5 points, so it's a Del-Pizza surface of degree 4. However, the 5 points to blow up are not in general position. You will create some -2 curves, and if you contract them, you will obtain a toric variety, which actually is a singular Del-Pizza surface of degree 4. And again, as it is a matter of fact in toric geometry, whenever you have only one integral interior point, the polarization is the anti-canonical polarization. Okay, so what is the case B moduli space in the toric setup associated to such a toric data, toric variety Y, D, and L? You look at all stable pairs, Y, D plus epsilon C, where your Y is a fixed toric variety, D is the toric boundary divisor, epsilon is a small number, and you vary all your curves C such that C is a curve in the linear system of L. If you're in dimension 2, and generally it's a hypersurface in the linear system of L. So in the description of the KSB moduli space, I said you look at all moduli space of stable pairs. There were 2 conditions such pairs needed to satisfy. For B, I'm taking D plus epsilon C. So I want this to have SLC singularities, and I want the B plus the canonical divisor to be ample. If I take B, D plus epsilon C, because D is anti-canonical, if I sum up with the canonical divisor, I will just be left with epsilon C. It's automatically ample. And one can check the SLC condition amounts to saying I want my curve C to be torically transversed. So one can check for some sufficiently small epsilon. This pair Y D plus epsilon C is stable is exactly saying that C is torically transverse in the sense that it doesn't pass through zero-dimensional strata of your toric boundary. In this context, around 20 years ago, Valery Alexiev proved that if you look at this moduli space, then the normalization of this moduli space is a toric variety, and the associated toric fan for this toric variety is a secondary fan for the momentum polytope of this toric variety. And I will briefly recall what the secondary fan is. For details, it's also known as the GKZ fan, GKZ fan, defined by Gelfand, Kapranov, Levinsky. So here's a picture of it. If you look at this lattice polytope for our DP4, the secondary fan corresponds to the fan of P2 that I drew here. It's the fan whose maximal counts are in correspondence with regular triangulations of your polytope. So here you can triangulate your diamond-shaped polytope this way or that way or that way, And each regular triangulation by regular, I do mean it's compatible with a piecewise linear function. So the regions you see here, you can be thought of the domains of linearity of a PL function. And if you look at all such regular triangulations, they're encoded in the secondary polytope. Sorry, secondary fun. Okay, so what Waller's result is saying, if you look at the storic variety, dp4, corresponding to this diamond-shaped, the case B moduli space is the toric variety whose fun is the fun for P2. So the case B moduli space is P2. Okay, so what we want to do is to understand the case B moduli space in the non-toric setup. Before that, I want to say a few words about why, even in the toric setup, the case B moduli space is toric, why there is a torus inside it, to illustrate Waller's statement. So if you consider all curves, or all divisors in general in a toric variety in the linear system of L, being in the linear system of L means they're defined by some equations with variables of the form z to b, your toric monomial basis. And if you assume that the coefficients are all elements of C star, so if they're defined by some AP z to p is 0, where APs are in C star, then you can check that all curves are actually elements of the case B moduli space, because as long as their coefficients are in C star, they will be torically transverse. So these curves, all these curves, naturally form a torus C star, where you just vary coefficients APs. You have as many APs as the number of integral points in P. Up to some reparameterizations and scaling, you will obtain a torus C star to the number of integral points minus the dimension of y minus 1. So the case B moduli space naturally does contain the torus and the toric setup. And what you want to see is, how can you compactify it in a nice modular way so that the boundary also parameterizes stable objects of similar type? And what Waller claimed and proved is the correct things to add are degenerate surfaces. So each of these pictures triangulations do define you the data of a toric degeneration of your y, so that each of these triangles, which correspond to P2s or weighted P2s, form the central fiber. You view them as the polytopes for the irreducible components of the central fiber of your toric degeneration. And what we showed is, if you keep track of how your curves degenerate under such toric degenerations of your toric variety, use some properties of your toric monomial basis to investigate that all curves actually, if they're torically transverse, they again degenerate to torically transverse curves. So this way he concluded, by using the nice properties of the toric monomial basis, that actually the correct right compactification is indeed given by looking at the secondary fan, and this moduli space is the toric variety corresponding to the secondary fan. So what we want to do is to obtain a similar result in the non-toric setup, where we no more have the data of a secondary fan, because we no more have a toric polytope. So what we first observed is actually there's a natural alternative interpretation of the case B moduli space in mathematics as the complex moduli space of a threefold. And I will tell you what that is. If you look at this threefold C, given by the equation uv equals f of xy for some Laurent polynomial f, then you can look at the Newton polytope of f, which naturally defines to a toric variety, as you mentioned. And if you look at the affine conic bundle of y minus d, where y is your toric variety, d is your toric boundary divisor, so y minus d is just a big torus in your toric variety. If you look at the affine conic bundle whose fibers are just C stars away from the curve defined by the equation f equals 0, and over the curve the fibers are uv equals f, this defines you a threefold. And as they explain in our paper, if you look at the complex modular space of this threefold, it amounts to varying the coefficients of f, but it amounts to looking at all possible curves, so you can naturally compactify this curve, looking at all possible curves in the linear system of L. So you can interpret the KSB modular space as this complex modular space of this threefold C. And then here mirror symmetry comes into play, and it suggests that this complex modular of complex structures on Z should be the same thing as the complexified modular Kähler modular space of whatever the mirror of C is. And by abuse of notation, we often say not the mirror of C, but the mirror family to YDL, because C is naturally associated to the state of toric variety. And just some words, if you're a physicist and the physics language, this curve here is often called the Sabak-Witten curve for the 4D n equals 2 theory obtained by compactifying type 2B string theory on Z. Okay, so here, in the toric setup, we can understand mirror symmetry rather combinatorially in an easy way. So if you want to tell what the mirror to Z is, which I denote by X bar, or the mirror family to YDL, mirror symmetry here is rather combinatorial in the sense that your Y was having this polytope, associated polytope, and I want to be mirror symmetry as the duality between the fan and polytope pictures. So to construct a mirror to Z, I will take the cone over the polytope of Y, and I will want to view it now as the fan of the mirror. So if you take the cone over the polytope of Y, you will obtain a singular toric variety X bar whose fan is this, and this will be the mirror to Z in this toric setup. However, as usual in mirror symmetry, we do not want to consider only the mirror to Z, we want to consider to maximal degeneration, the mirror to a maximal degeneration. And this will be obtained by taking all possible crepant resolutions. In this case, I have only one crepant resolution, which gives me the smooth variety X, which is a projective crepant resolution over X bar, which I declare to be the mirror to Z. In this case, it's the canonical bundle of P1 times P1. Okay, so just to recall, the expectation from mirror symmetry was that the KSB modular space should be a toric variety whose toric fan should be given by all the Kähler cones of all possible crepant resolutions. In algebraic geometry, a Kähler cone is the same as an ample cone whose closure we call a Neff cone, which is the cone of non-negative cone of Neff divisors, which have non-negative intersections with effective Kerr classes. And you can ask, if you consider all possible crepant resolutions of your singular toric variety X bar, if you consider all possible Neff cones, will they form a toric fan? And it was shown some years ago by Jean Kiel, if you have a nice space, what he calls the Mori dream space, then you can naturally define a complete toric fan. And I will tell a few words about this soon. And this fan is called the Mori fan, whose maximal cones are all Neff cones of all possible crepant resolutions, together with some additional cones, which he calls bogus cones. They are bogus in the sense that if you do understand the birational geometry of all crepant resolutions, you can tell what these cones are that you need to add to obtain a complete toric fan. So in our example here, if you look at our toric variety, remember I drew the secondary fan P2, which correspond to all triangulations. The data of these triangulations, apart from defining the durations of Y, combinatorially do define a second thing. So, namely, if you take the cones over these polytopes, you obtain, on one side, you obtain your X, which is the smooth projective crepant resolution. If you take the cones over the other triangulations, You will obtain some varieties with some orbifold singularities, but they're all related to your x by some divisorial contractions. So here, when you just take the nefcon of your Crepont resolution, you will obtain A2. But if you know all possible divisorial contractions on x, which amount to, here in this case, there are two divisorial contractions. You can contract a P1 cross P1, which will give you x prime, or another P1 cross P1, which will give you this x prime prime. And such divisorial contractions means you're going to the boundary of the nefcon of x, and then you can describe a bogus cone by adding an array corresponding to generated by whatever divisor you contracted. So knowing all divisorial contractions of all possible Crepont resolutions allows you to describe some additional bogus cones and to obtain a complete fan. And it's a result of people working in a minimal model program, namely Birka, Kashina, Haken, McKernan. If you have a Crepont resolution of a canonical singularity, you can always describe this Mori fan. There are always a Mori dream space, which allows you to do this. And the secondary fan is exactly equal to the Mori fan of the mirror, as in this example, they're both P2. So in particular, what Valery proved in the toric setup by describing the KSB modular space as a toric variety corresponding to the secondary fan is actually justifying a prediction coming from mirror symmetry, namely, it's the toric variety whose fan can be described by considering analogs of all Kähler cones. So it's the toric variety with fan, the Mori fan of the mirror. We will use this interpretation because we want to obtain a similar result in the non-toric setup. There is no more notion of a secondary fan, but we will define analog, a generalized secondary fan in the non-toric setup as the Mori fan of the mirror after we describe what it does mean to have the mirror, after we describe what the mirror in the non-toric setup is. So the non-toric setup I want to look at is the setup of local Abel surfaces. So here I will fix YDL, which is a polarized local Abel surface, given by a projective surface Y, which is not toric necessarily, and an anti-canonical device, the DNY, which is reduced. And generally, people call local Abel surfaces when very smooth. We are a little more flexible. We want to impose the particular singularities to spare. If you assume very smooth and these normal crossing, they fit into this situation. In general, we impose the pair YD to have so-called low-canonical singularities. And L is, again, an ample line bundle on Y. And furthermore, we assume that YD is maximal, which by definition means D should be non-empty, so we don't look like K3 surfaces, for instance. And D should have at least zero-dimensional strata, so we don't consider situations like P2 and the smooth elliptic curve. So D should be singular. So there are infinitely many such surfaces. So particularly, any toric variety together with the toric boundary device is a local Abel surface, but there are infinitely many more such surfaces. You can blow up any number of points on the toric boundary divisor to obtain, and you can look at the strict transform of your toric boundary divisor to define D. So the pair whose total space is a blow up together with the strict transform of the toric boundary will give you a local Abel surface. And associated to such surfaces is a natural generalization of what the toric momentum polytope is, known as the Symington polytope. So if you're a symplexic geometer, you want to view the toric momentum polytope of a toric variety as the base of a torus vibration, like this triangle you can weave it as the base of a fibration on P2, where the general fiber of any point in the interior of the triangle is a torus. A Symington polytope associated to a non-toric local labial surface like this, where you obtain as a blob, is an integral affine manifold with singularities. So if you do a non-toric blob, say on this side corresponding to a divisor, then you chop off a triangle and you glue the remaining sides of the triangle. So this way you obtain an integral affine manifold where the invariant monodromy direction I just drew as this line which is parallel to the edge where you blow up. So again, on an interior point, you can realize your fiber as a torus, where over this tip of the triangle, you get a degenerate fiber. Other examples of local labial manifolds, apart from doing this non-toric blobs on toric to toric manifolds, there are other ways to construct such local labial surfaces. So in this situation, we will call the toric surface we started with a toric model, and you can obtain a local labial surface by starting with a toric model and doing non-toric blobs. But another way to obtain them is just to start with a toric pair given by a toric variety together with its toric boundary divisor, and then to destroy the toric boundary divisor. So in P2, your toric boundary divisor will be a union of 3 lines. And if you say smooth one corner, one line, one intersection point of these lines, you can consider P2 together with an anticanonical divisor given by the union of a line and conic. And this will again define a local labial pair. There's again an associated Symington polytope where you have one singularity again with monodromy invariant direction that I drew as in the figure. So you can imagine as smoothing this corner on the toric boundary. And the fact that there is always such a picture is related to the fact that there is always a toric model. And the situation where you just blow up a toric variety is easy. It's just a toric variety you start with the toric model. But Grosek and Kiel showed that any local labial surface has a toric model. Namely, it can be obtained as a blow-up of a toric surface at smooth points on the toric boundary, up to some technical details. So you may not always have enough -1 curves to contract in your local labial to get a toric variety. But up to doing some corner blow-ups, you can always do that. So up to some corner blow-ups, which means the 0-dimensional strata of D, if you blow that up, you can always obtain your local labial surface as a blow-up of something toric. In this example above, your toric model is P112. I claim if you start with P112, and if you do a non-toric blow-up on one side, which amounts to chopping off this white triangle, then you get what I drew in the picture, but you push in a singularity with monodromy invariant direction parallel to that edge. So you always have a toric model and an associated Symington polytope, which realizes the base of a normal toric vibration on your local labial surface. And thank you. Related is the fact that you can, again, consider this picture here. In the toric setup, phi minus t was just a torus. Here, again, as shown by Gross, Hacking, Kiel, the complement will not be a torus, but a cluster variety. So up to a codimension 2 locus, you can cover it with many tori, and you can, again, just consider this affine conic bundle of your Seiberg-Witten curve. And you can ask, how can we describe the mirror to Z, which we did easily in the toric setup combinatorially? Now, what is the mirror to Z, and what is the Morifan? So I will tell you this after providing the definition of the KSP moduli space in this setup. MYDL here Similarly as in the toric setup, is the locus of stable pairs yd plus epsilon c, where c is a curve varying in the c is any curve in the linear system of L. And in the toric setup, there was no complex moduli of yd. Here, depending on, here you can move the points you blow up in your toric model. So here, in addition, you have you look at deformation equivalent pairs to yd plus epsilon c. And we claim this moduli space is still toric. Again, the two conditions of being a stable pair, the second is automatically satisfied. And again, C needs to be transverse. It shouldn't pass through zero-dimensional strata of D to have a stable pair. And we do prove in our work with Valerie empiric that this moduli space of all polarized colabial surfaces up to a finite cover is a toric variety. So in the toric setup, you can sort of believe it should be a toric variety when you start with a toric variety. It's something already combinatorial. The moduli space, you can combinatorially show that it's again a toric variety. In this setup, what you start with is a polarized colabial surface, which is not toric. And so it's a surprising result that you end up with a moduli space, which you show is still nonetheless toric. And this is a conjecture of Hacking-Keel-Yu. It was conjectured first by Keel that it should be a toric variety around 2012, and Hacking-Keel-Yu made this conjecture more precise by saying there should be a generalized secondary fan. And known cases where this conjecture was proven by, apart from toric varieties, just 6 Dalpitzel surfaces of degree n, where you fix your anticanonical boundary to, where you fix the pair yd, where d is n many minus 1 curves. In these situations, the Simix impoitope again has only one interior integral point, and they're all self-mirror, in the sense that the dimension of the complex and scalar moduli spaces are the same. So there's not really much mirror symmetry going on. So we prove this conjecture for all possible Dalpitzel surfaces. And I will tell you how the proof goes. So here's the strategy of the proof. So we start with a maximal degeneration of YDL. Similarly, as in the toric setup, we want to understand mirror symmetry. We want to construct a projective Crepont resolution, x over x bar over one-dimensional space. And we call this the semi-stable mirror construction. The so far known mirror constructions in the maths literature did not cover this case because there's the Gross-Hacking-Keel mirror symmetry for low-calabial surfaces would tell you how to construct a mirror of a single low-calabial, but not to a maximal degeneration of it. And more generally, Gross-Siebert would tell you how to construct mirrors to maximal degenerations of calabial surfaces under the assumption that they are log smooth. But in the case B moduli space, such maximal degenerations we consider are not satisfying this assumption. And then there are some non-Archimedean approaches to understand mirror symmetry under the assumption that the complement y minus d is affine due to Keel and Yu, which again does not work here. So we developed this framework of semi-stable mirror construction, and I will tell you how we do that. And then once we obtain the mirror x over x bar, we show you get a Mori dream space, and in this case, you can apply the Gross-Siebert mirror symmetry. You can construct a Mori fan once you know it's a Mori dream space, and using the intrinsic mirror symmetry of Gross-Siebert, you can construct a mirror family. So we construct a mirror, this Crepont resolution, and we look at the double mirror, where this way is now by applying tools of Gross-Siebert, to construct a double mirror family over the toric variety whose fan is the secondary fan. And then we show that this family, the double mirror family, is a K-space stable family, and furthermore, the general fiber is the formation equivalent to what you started originally. So this way, we show that the toric variety M-sec corresponding to the Mori fan of the mirror we construct thus parameterize K-space stable pairs. In good situations, it is a K-space moduli space due to some technical issues. Sometimes it is just a finite cover of the K-space moduli space. Okay, so here's an overview of how we construct a mirror. We start with the maximal degeneration of YDL, our polarized colabial surface. It's a degeneration of it into a union of copies of P2s. We show you can obtain such a degeneration by considering a regular triangulation of your associated Symington polytope. Similarly as in the toric setup, here all triangles will correspond to P2s forming your central fiber. And then we explain a version of Legendre duality. So we want to view this picture, this triangulation of the Symington polytope, as the intersection complex of your degeneration of Y. Our mirror symmetry suggests it should be the dual intersection complex of your mirror degeneration. So we want to construct a normal crossing surface first, whose dual intersection complex looks like this, x0. And then we want to smooth this normal crossing surface to obtain our mirror family. So the hard part is starting from a surface, starting from a triangulation to first construct a normal crossing surface, and then to whose dual intersection complex is this, or we describe some sort of duality whose intersection complex will be obtained by taking the toric dual and pushing in singularities. And then we want to smooth it. So we start with a nice Symington polytope, which makes life easy for us due to Engel Friedman, who say that you can always obtain a Symington polytope associated to any local labial surface by starting with a toric polytope where there's a central point, and the triangles you chop off from your toric polytope are on the sides like here. And our first result is rather combinatorial. We show you can always describe a triangulation on such Symington polytopes which define a maximal degeneration of YDL. And such that, like, this triangulation describes the intersection complex of Y0, the central fiber, which we want to view as the dual intersection complex of a normal crossing surface x0. Then we construct this normal crossing surface to each vertex here. If you look at the fan, they will define the toric variety, which give irreducible components of your normal crossing surface. If they're on the boundary, they will be non-complete toric varieties. If you're at the tip of a triangle you cut off, we need to do some deformation theory to describe those components. Okay. And then we'll see how this normal crossing surface, like here as in the example of P2 with a line and conic, this left-hand side is the intersection complex, the Symington polytope of Y. If you describe the dual, I just take the toric dual and I just push in a singularity from the edge corresponding to where I did a non-toric blow-up. So your intersection complex will be, so you forget that edge. And that part here will give you a copy of A2. This will give you a copy of A2 on the right-hand side, and you will get another copy of P1 times A1. So your x0 normal crossing surface is the union of these, where the P1 cross A1 has a destroyed toric boundary, non-toric boundary. Once you have this normal crossing surface, we do some deformation theory. This is the technical part. We show you can glue all these components, irreducible components, in a way you can apply log-smooth deformation theory to describe a smoothing, a semi-stable smoothing, such that x0 sits inside the total space as a normal crossing divisor. And so that the total space is projective with a trivial canonical bundle. And furthermore, we show there's a contraction from X to some singular variety, which has canonical singularities. So in particular, we reduce, by this construction, we obtain a Mori dream space. And now we can construct the associated Mori fan, and the claim will be the corresponding toric variety associated to the Mori fan of this total space will be the will parameterize the K-space stable pairs. So step 2 is to recall, so once we have this mirror, as a second step, once we construct the associated Mori fan to the mirror we construct, we want to construct a family over the toric variety by taking the Gross-Seibert double mirror. It will be the topic of Mark Gross, the second mirror here. Gross and Seibert show that whenever you have such a nice family, like our semi-stable mirror, you can associate to it family given by the approach of what they call the algebra of theta functions. So it's the approach of an algebra where coefficients are living in a formal scheme, form a power series with variables, elements of the Mori cone, which is the cone of effective Kerr classes. And theta p is a Gross-Seibert theta function. So unlike in the toric case, we do not have a monomial of basis of sections of this mirror, but we can define a basis of theta functions which generate sections of a natural line bundle on this mirror. There are Gross-Seibert theta functions, and the structure constants are described using enumerative geometry. Again, I will leave it to Mark to tell more about this construction. Due to Abramovich and Gross-Seibert, there's a log-Rameau, punctured log-Rameau written theory, which tells you how to describe the structure in this algebra. So here there are some subtleties to apply this construction, which works for projective families, to our setup. So we generalize this a little bit. And then on key pointers, we show that there are some convergence properties. So you don't only have this approach over some formal ring, but you get a Beer family over toric varieties, spec C and EX. And we do this for all possible Crepont resolutions, X. But we don't only want to get the mirror, we also want the mirror together with the divisor and the curve to talk about stable pairs. So we show, if you look at all theta functions, by taking points corresponding to points in the interior over the cone of your Symington polytope, this will define an ideal, so you will get a natural divisor in your Y. And there's a natural line bundle where you can define, again, a curve in the linear system of this line bundle. So we consider these tuples, and we run the intrinsic mirror construction for all possible Crepont resolutions, and we glue all these mirrors, Y, D plus epsilon C together, eventually to describe a mirror family over the toric variety. And the gluing argument here uses recent work of Mark Gross, gluing formulas in punctured log-Rameau written theory, where similar arguments can be found also in the current ongoing work of Gross, Hacking, Kiel, Seibert. And at step 3, we show that this mirror family, the key technical part is to show the double mirror family is K-space stable. And furthermore, the general fiber is the formation equivalent to what you started with. So let me see how much time has remained. Okay, so showing this over the torus inside your toric variety is not very difficult. We show that theta functions admit similarly nice properties as in the toric monomial basis case. And over the boundary, there are some technical issues to show this. And to show that the general fiber of this double mirror is deformation equivalent to your original YDL, we show it's diffeomorphic and apply previous results of Friedman. Finally, once we have this double mirror family over the toric variety by universal property, this gives us a map from the toric variety to the KSB moduli space. We show that this map is finite and surjective. And I will not tell you too much about the proof, but in this finiteness comes due to the issue of ordering or non-ordering the points you blow up in your toric model to obtain your YDL. If you blow up only one point, or if you're in a situation like in this example we were discussing where P2, where you consider P2 with a non-toric boundary, where your mirror has intersection complex this. In this example, there's only one parameter family of compact curves in this component P1 times A1. The Morifan is rather easy to describe. It's only P1, the Morifan, because you have only one Neff cone and you have one divisorial contraction where you have one bogus cone generated by this P1 times A1. In this example, the KSB moduli space is just the moduli space corresponding to the toric variety, which is just P1. So it parameterizes all lines which vary, and generally they look like in the middle. And as in Gromov-Witten theory, when your points tend to go to the singular point, things break up. And you can check this is the correct moduli space. Just in the last 2 minutes, I want to say so this proves the main thing we wanted to prove, that the KSB moduli space is toric up to a finite cover. But when we proved this, going through all this mirror symmetry, describing the mirror and the non-toric setup, we noticed we also answer another question in physics about some quantum field theories, namely 5D superconformal field theories. So in physics, mirror symmetry says that if you look at type 2B string theory on R4 times R threefold C, which was this affine conic bundle I drew, this is the same for the n equal 2 theory if you look at the type 2A string theory on R4 times the mirror to Z, which I denoted by X bar. And essentially by description of M theory, this can be described as doing M theory on R5 times this X bar. You can obtain it by compactifying this M theory along on a circle. And recently, there has been much progress on this question of looking at 5D superconformal field theories obtained by webs of brains, and then showing the same description can be obtained by doing M theory. So the known situation, if you look at 5 brains in type 2B string theory, you can describe a 5D n equal 1 superconformal field theory. And string dualities will tell you there's a correct X bar. You can obtain it by doing M theory on R5 times X bar, which is the X bar I described in the toric setup. And if you rather start with 5 and 7 brains, you can again obtain a superconformal field theory. And in this setup, it was not known what the correct X bar is to get the M theory and describe this 5D superconformal field theory. And it will be the topic of Pirik, who will explain the semi-stable mirror we construct is the correct thing. Thank you very much.
So in the toric case, the secondary fan is equivalent to the Mori fan?
That's true, yes. this follows directly. If you look at the book of Cox-Siddle-Shank toric geometry, if you read through the description of what is the nav divisor and the toric setup, it just follows from the standard arguments of toric geometry.
Oh, okay, so you can see like automatically how you get from a triangulation
Exactly,
to a,
it's
okay.
standard toric geometry. You can directly see that, yeah. Thank you.
Any more questions? So let's thank Julia again.
Thank you.
Now there will be another break in the terrace, coffee break. We can reconvene at 4:30. How is it going?
I think
The battery is...
I'm sure it's on and off. Maybe we'll save them for tomorrow if they are. Oh, this is the only thing you have.
Sorry?
These are the only ones.
No,
you
no,
have
no, I was
still.
switching it off. Yes, I think that there are no other batteries. Well, I don't know. Here, but... I mean, they will be charged for tomorrow.
Oh, okay. I think it's.
Hello, hello.
I microfoni qui si possono
Ah sì,
aggiungere.
erano accesi, li ho spenti adesso.
Ok,
Erano
perfetto.
accesi.
Test microphone.
For 30.
Oh, is it for 30? Ah,
Yes,
so
because I
nice.
said on the microphone. Yeah, no, because we went a couple of minutes long. It's better to let people. You can put it here in the center.
How's this?
Test. then I'll turn it back on.
Sorry, so this is the pointer, so forward and backward.
And then is this the laser pointer?
Yes, and it's, I mean, you can point there or here is the same. I mean, in fact, you can put wherever you want. It works anyway.
Okay, but
It's an accelerometer, so you can put over there. It's the same. It works always.
Okay. Wow. Oh, these are to make sure that I end on time. Yeah. Great. Yes. No, for the last talk of the day, it matters more because I'm what's keeping people from dinner. So yeah, I was planning on just keeping my eye on the clock, but yeah, just wherever. Yeah. Thank you so much. That was. Uh-oh.
Okay. Control.
How did I do that to make sure I don't?
I'm not sure. Oh,
Okay, cool. So that works. And then this is. Okay, cool.
Would you like me to also say something about the poster session, or you will be saying after?
Yeah, I was going to ask Agnese Bissi to say something because I don't know. Yeah.
I saw there is.
Yeah, there is a poster. Yeah, I know.
Just
Yeah,
remind people.
Yeah, you can see there is a poster session, and then I don't know if
Oh. Maybe you would like to say about it. It makes more sense. So our next talk is by Arun Debray, and it is about anomaly cancellation in string theory from homotopy theory.
Hello, is my microphone on? Yes. Okay, cool. Well, I just wanted to say I just like to thank everyone so much for the opportunity to speak here, and I hope you enjoy my talk. So I'm going to talk about, as mentioned, anomaly cancellation in string theory using homotopy theory, specifically Bordism. And so the idea of this talk is using, you have a question in physics. Here's a theory of some sort, maybe a field theory, maybe a supergravity theory. It has an anomaly. Is that anomaly trivial or not? And what I want to convey in this talk is how to go from that question to a precise math question, and then solve the math question. And then, going back to physics, what does that imply? So, I don't know string theory very well, especially compared to everyone here. I'm a mathematician. I specialize in the mathematical computations, the homotopy theory that makes this happen. And so, well, first of all, I'd like to thank this list of collaborators who I've had a lot of fun working with and who have taught me the string theory that I do know. And so hopefully, well, I think hopefully the style of the talk, let me try that sentence again. Yeah, so I tried to write a talk that struck the right balance between physics and math. Hopefully you will also find that to be the right balance. So let's see, there's what I'm talking about. I'm going to mention a couple specific projects with Marcus D. Riegel, Jonathan Heckman, and Miguel Montero, a project with let's see, Ivano Basile, Matilda Delgado, Miguel Montero, and then a couple projects and some ongoing work with Matthew Yu, who is here. So why don't I go ahead and get started? So as I said, the goal of this talk is to take some tools from algebraic topology and solve some math questions which have some interesting consequences in string theory. And what do you want to get out of this talk? So one potential thing for you to get out of this talk is, well, what is Bordism and why should I care about it as a string theorist? Another question which I sort of alluded to is, well, I as a mathematical physicist am in the business of looking towards physics as inspiration for math theorems to prove. So in this setting, what does that look like? And building on those, another question might be, well, okay, so given that, what is being done? What do people know? What's easy and what's hard? Or maybe what's easier or harder? And the thing about this kind of calculation, this sort of deal is, there's a lot of different ways you could do this problem. There's so many different theories that people study, quantum field theories, supergravity theories, string theories, and various symmetries you could put on them. And so there's an enormous number of calculations you could make. So how do you know before trying a calculation that it's a reasonable calculation to try? How do you know going in that it's not going to be insanely hard? So some terms and conditions apply. At this point, I should mention them. So the first one is, people mean lots of things in physics by anomaly. I am by no means saying everything about anomalies, and I don't want to give off the wrong impression. So people sometimes say 't Hooft anomaly for the kind of thing I'm going to talk about. And if at some point you're thinking, wow, for what he's saying and my conception of anomaly, none of this makes any sense, then what's most likely is that there's it's just different things under the same umbrella, and that the tools that I'm using don't apply to that case. Another thing that I should mention is, I'm going to say anomaly of string theory a lot. And this is kind of a mathematically contentious phrase. So I mean this in the sense of, putting on the mathematician's hat, where if you say theorem, everything should be precisely like, well, this thing is precisely defined, and the proof in principle could be broken into steps of mathematical logic. And okay, if you say this, and then you say anomaly of a string theory, the obvious question is, what do we mean when we say the anomaly, like what do we mean by string theory? And so, if you want to say the anomaly of a quantum field theory, you can say, okay, before I take the path integral, I have all this formulations. Like I have the fields, I have, maybe I have an action, and that much is mathematically defined. So talking about an anomaly there is okay. But with string theory, this is even hairier. And so I shouldn't do that. So sorry in advance for doing it. When I say that, I'm going to mean, let's look at the, mathematically precisely, we're looking at the supergravity low energy limit, where you can really say this. And so now if I'm talking about that, well, anomalies are things that we evaluate on a space-time manifold. And evaluating supergravity on a space-time manifold, again, if you say that, it sounds a little funny. And so, before in supergravity, you do this sum over various backgrounds. And so this story is taking place before you do that. So hopefully with these disclaimers, things will be all sound. But if anything seems up, please do let me know. I'd rather know about it. And then we can try and figure out what the common ground is. So I've noticed that if you ask 4 people in mathematical physics what an anomaly is, you should expect to get at least 5 answers. I'm going to give you 1. Well, a little less than 1. So let's say that you have a group acting on a vector space. You have a representation. In particular, I'd like to draw an S right here. Let's see if I can do that with I cannot do that with the pointer. So pretend that it was a vector space, not a vector pace. I'm sorry about that. So I'm glad the pacing of the talk is going well, at least for a start. So, okay, a group acts on a space, a vector space. You've got a representation. And what do we know? Okay, it's through linear functions. They send lines to lines. And so what that means is they send points to points when we pass a projective space. Okay, great. But you can't go backwards. if I have a group action on projective space, there's no guarantee that it lifts to a linear action. So the famous example is the spin 1/2 representation of SON, which is only a projective representation, and so you've got a nice action on say, CPN that does not lift to Cn+1. You know, alternatively, you could say, well, what if I lifted to the spin group? But that's sort of a separate story. So this is really a fact about, like, this whole thing is really a fact about quantum mechanics. So quantum mechanics is projective. This, you know, really we should be, you know, when we talk about states in quantum mechanics, we're talking about the projectivization of the thing we usually call the state space, the Hilbert space of states. But what do people do? What do we all like to do? We work with the Hilbert space. And various constructions actually require working with the Hilbert space rather than projectivizing. And so, for example, gauging asymmetry. So if you have an action and if you have a symmetry of the theory in the sense that it sends states to states on the projectivization, but it does not lift to the Hilbert space, well, that's kind of a headache, because the way we prefer to work with quantum mechanics, or at least I prefer to work with quantum mechanics, is incompatible with the symmetry. And so that is an example of an anomaly. It's a projective G action that does not lift to a linear G action. Okay. So what we'd like to do is bring this concept from quantum mechanics into quantum field theory, quantum gravity, et cetera. And so we need to sort of make this work. You know, you need to be able to feed spacetime to this story. And so now what do we have? We have associated to each choice of background spacetime manifold, we've got some sort of obstruction. And it ought to be, like everything in quantum field theory, it ought to be both local and unitary, whatever that means, which I have not and will not define right here. But this is some sort of function on spacetime manifolds. It's local and it's unitary. Okay, so you know, you might be thinking, I know lots of things which are those.
Since you're talking about the Hilbert space and its projectivization, shouldn't you be using the word space, not space-time there? When you said you have such an obstruction at each point.
Oh, this is a good point. Let me see. You are exactly right. Yes, okay, let's say space here, and sorry about that. Okay, so yeah, thank you for the correction. Let's say space here. There's other ways to think about anomalies where you start with what's going on with partition functions, and it seems like I got the two mixed in my head, so sorry about that. Was that the extent of your question? While we're stopped, has anyone got any other questions? Okay. So, all right, we've got some data which, you know, whatever the obstruction is, wherever that lives, it's something. It's, you know, that something actually ends up, it's an element of a cohomology group, so it's got some sort of linearity structure. It's local, it's unitary. And so following that line of reasoning, you might guess that the anomaly itself is a quantum field theory. Or, sorry, is a field theory. And there is a way to make sense of this precisely through what's called anomaly inflow. And so I learned this through the mathematical incarnation of a relative quantum field theory, which is due to Fried-Telemann. So the takeaway is the data of these obstructions assemble into a field theory, but if you started off with an n-dimensional field theory, the anomaly is in n+1 dimensions. So in addition, you know, it's not just any field theory. It's got to be pretty simple. It's got to be very, very simple. And the condition that ends up happening is that these spaces of states of this field theory are one-dimensional. And so such a theory is called invertible, which is a notion defined by Dan Fried and Greg Moore. So technically, the definition of invertibility A priori, it's not the same as what I wrote down here, but in all reasonable situations, they are equivalent. So, okay, now I want to know what are all the possible anomalies, which means I want to know what are all the possible, well, unitary invertible field theories, but since the mathematical way people think about this is more typically in Euclidean signature, you end up wanting to discuss reflection positive invertible field theories. And now something wonderful happens, which is someone's classified them all. So this is the theorem. It's got some symbols that like I have not yet explained, so that's what I'm going to do next. But what I want to show you is the like a couple salient features, like the structure of this theorem, and then we'll discuss the pieces, and then we'll see the theorem again. So Dan Fried and Mike Hopkins did a large part of this, conjectured the non-topological part, and then Dan Grady proved the non-topological part. So first of all, what is there to say? That if we pick a dimension and we pick this psi structure thingy, which I'll say about in a minute, then invertible field theories are an abelian group. So that's already a nice salient feature. And so, and that structure is tensoring them together. So, okay, there's that. And if you know them, if you want to know what that is, oops, that is not what I meant to do. Well, you can get that by obtaining some other abelian groups and putting them into a short exact sequence. So we need to figure out what those other abelian groups are. And, okay, so you want to know what the possible anomalies of a quantum field theory are. You calculate the sub and the quotient groups. You say, very good. You check how they extend. That extension is actually always going to split. And then you know what the anomalies are. So let's figure out what these things are, these omegas. And then we'll be able to calculate what anomalies are, and then maybe actually address the anomalies themselves in some cases. So that's the name of the game. Wait, C modules? I think the best answer to your question is that I think that is not literally true, but it's like very close to being true. Like what's a good way to think about it? So one way in which this appears is, like this looks sort of like it came from an exponential exact sequence, right? Like this hom into C star could be replaced with like x into z and then hom into z. I think it's a good analogy even if it's not literally true. Sorry, I don't have anything more precisely to say right here, but hopefully that helps. Yes, okay. So in this formalism, so I was not planning on getting really into the weeds about this, but mathematically when people talk about topological field theories, there's a Bordism category and there's a functor to something like vector spaces. And we're looking at fully extended theories, so these should be higher categories. So reflection positivity. Reflection means there's a Z2 action on the domain and the codomain category, and I want equivariance data for that action. And positivity says something about the partition functions on manifolds which are obtained by taking two copies of a manifold and gluing them together along their boundary. So yeah, so that's what that looks like. That definition works for the invertible case, but it seemed like generalizing that to the non-invertible case is something that people are still working on. Who's got more questions? Okay. Case. So the first part, this psi that I mentioned, is what's called the tangential structure. So it's basically what are the fields? So if I've got a theory with fermions, like what fields are needed to make this make sense? You better have something like a spin structure. Maybe you have like a spin C structure or something, but the point is you have to, based on the data of the theory, you need some structure. You need a spin structure if you want to have fermions. You need maybe you have a principal U1 bundle so that you can do U1 gauge theory, things like that. And so Xi is saying, why don't I keep track of all of that? It's precisely the notion of tangential structure. And the thing to keep in mind is that this is topological. There's no metrics, there's no connections, there's just the topological part of this structure. So if you have if you have a background SO3 symmetry, yes, you need to couple to a connection to do that in physics, but we're leaving the connection out. We're just looking at principal SO3 bundles. So, and again, the point is, in order to do physics, you have to specify what dimension you're in, and you have to specify what structure is present on space-time. So now I need to say what the heck this is, this omega n psi. N is the dimension, psi is the tangential structure, so what's omega? And so this is what's called a Bordism group. And so what we do is we say, okay, great, I'm going to take all possible n manifolds that are that are closed, right? So this should be an element of omega 1 SO. SO is saying that I'm looking at oriented Bordism. And I'm going to say all of these things become a commutative monoid under disjoint union. This is a very big monoid. And now I want to say, actually, let's kill the ones that are boundaries. Why would I do this? Well, there's various reasons. First of all, I think it's cool. But second, the monoid goes from very big to very small. Very small. So usually it's not zero. But when you do this, if psi is reasonable, then this is always a finitely generated, well, it turns out actually an abelian group. And so the idea is, I want to take a manifold and its inverse, right? I always want to be able to take something and make sure that their disjoint union is a boundary. That way I know that I have a monoid with inverses, also known as an abelian group. And so the answer is always M with the opposite psi structure. So in this case, it's going to be the opposite orientation. You know, if it was a spin structure, there's a notion of opposite spin structure, et cetera. And so there's a procedure for defining the opposite structure in general. So in doing this, you therefore obtain that this thing is actually an abelian group. And that's good, because they're easier to work with than monoids. And so this thing is called the n-dimensional psi Bordism group. If you have heard the word cobordism and you're wondering how it's related, this is this thing that like people do sometimes where they say, like confusion of notation, but Bordism and cobordism more or less mean the same thing. Sometimes people use them for different things, but I'm not gonna. So so don't worry about the difference between those. Probably the only time a mathematician says this and co-this are the same. So now let's go back to this theorem. So what we've learned is that the group of invertible field theories is, well, there's a torsion part, which is homomorphisms from this Bordism group. So functions on manifolds, closed manifolds, which are multiplicative under disjoint union, and which vanish on any manifold which is a boundary. So, you know, you might be thinking about Stokes' theorem as an example of this. And, you know, we can take that thing and hom it into C star, and then we can take this other thing and hom it into Z. So we want to calculate these Bordism groups, because once you know a finitely generated abelian group, homs into C star and homs into Z are pretty straightforward. And then there's the question of the extension. But I have a torsion group and a free group and an extension here, and that extension has to split, just non-canonically. So if we want to know, I have a theory, what are all of its possible anomalies? Well, let's calculate some Bordism groups, and then we'll have the answer. Moreover, this short exact sequence that I just sort of threw up here has physical meaning. So let's say that you have a theory, a quantum field theory with an anomaly. Well, how might we access it? What's the first thing we do? Work perturbatively. And if you work perturbatively, you end up discovering something called the anomaly polynomial. And the point is that the perturbative information is what's left when you pass to the quotient. So people might call that the local anomaly or the perturbative anomaly or something. But there's also stuff that's invisible, right? So let's say that you know that the perturbative anomaly is 0. Let's say you've killed the anomaly polynomial somehow. Well, there's still some information here. There's some non-perturbative information, sometimes called the global anomaly, and that is still present. So this is why this, like, part of the reason I like the methods I do is because they don't care. They are equally good at them. And, you know, people, not me, are very, very good at perturbative things. So it's nice to have methods which complement that. So if you're wondering how n and n plus 1 became n plus 1 and n plus 2, if I have an n-dimensional theory, the anomaly is n plus 1 dimensional. And so we had to shift this thing up 1. So as I mentioned, you know, people have, like, for the typical examples I'm going to talk about, you know, the perturbative story is understood. Like, someone came along in the 80s and said, if you do this, this, and this, then your perturbative anomaly is 0. So therefore, this thing is solved. And as I mentioned, there's a global anomaly question too. And so that's what I'm going to focus on. Yes?
So as you said, there is no canonical choice of splitting, right? So it means that there is no canonical way of deciding which part is global and which part is perturbative.
Yes and no. So, well, yes, sorry. So you're right that you can't split it. But if you know something is 0 in here, then you know that it pulls back here.
Okay, I understand.
So you're absolutely right. I can't say here is an anomaly, here's the global part, here's the perturbative part. But if I've trivialized the quotient, then I know that I'm in the sum. Does that address your question? Great. Who else has questions? Okay. So, okay, we're back. We're in the sub. So that means that we should be studying Bordism invariance, these homomorphisms out of omega n plus 1. You know, landing in C star. So as I mentioned, let's figure out what this thing is. How does this point? I was pushing the wrong button. How was that? So let's figure out what this is. And using that, if you have some theory that you're interested in, once we know what the group is, once we know what manifolds represent generators, now we can understand the anomaly better. Typically, we want the anomaly to go away, and so we can just calculate it on the generators and see that it does that. So one of the best case scenarios that you can be in is you can say, wow, my Bordism group is 0, therefore there cannot be an anomaly. You didn't have to do any thinking, you didn't have to do any calculation, you just said, look at that. There's no anomaly because there can't be one. And so, okay, what's really going on is that all the hard work was in that theorem that said, well, okay, this thing is a Bordism invariant, right? That carries some significant information. And maybe this calculation is harder in higher dimensions. So, you know, this is the happy answer, where you don't have to worry about anomaly cancellation. It sort of comes for free. So I mentioned omega 1. Another example is oriented two-dimensional Bordism, right? So think about the best donut you've ever eaten. Maybe it had multiple components, right? You know, some donut shops sell multi-hole donuts. And think about the boundary of that donut, right? The outside. So every surface of genus G, no boundary components, is itself a boundary where you fill it in with the donut material. And that, you know, that is a delicious proof that the Bordism group there vanishes. So if I had a one-dimensional theory on just with only an orientation as the fields, then its anomaly must vanish because, well, there's nothing in the second Bordism group. So, you know, somehow you didn't have to work very hard in that case. So here's a case where one would have to work a little harder, which is the E8 cross E8 heterotic string. So in particular, we're in 10 dimensions now. And so now the nice geometric reasoning for Bordism groups is essentially impossible, and people calculate them in other ways. So what do we start with? So what is this string theory? We've got the data, we've got some fermions, so we better have a spin structure. And we've got E8 cross E8, which means two E8 bundles, P and Q, going to M. And now I said we better work in a situation where the perturbative anomaly goes away. So this is the Green-Schwarz mechanism. And what it says is that if you assume that the following is 0, better actually is to say that I have provided data trivializing it. So you might say, okay, this is a cohomology class, so let me produce a cochain which witnesses the fact that this is a coboundary, right? By taking the coboundary map. Or you might think of this as a map to KZ4, and you want a null homotopy of that. Data trivializing this. Just like an orientation is a trivialization of W1. So what is this? Well, if I have a spin manifold, then the first Pointrogin class is canonically 2 times some other class, which I like to call lambda. You might like to call it 1/2 P1. And C is, well, if you have a compact, simple, simply connected Lie group, H4 is canonically Z, where you can distinguish 1 from -1 by insisting that the killing form is positive, or under this isomorphism. And so, okay, so we've got a canonical characteristic class of E8 bundles, and I'm going to call that C. So what I need to know is I throw in this condition in the cohomology of that. So all of this data, which is an example of what's called a twisted string structure, all of this data goes into the definition of Xi. The spin structure, the E8 bundles, the degree 4 Green-Schwarz data. So that's Xi. And now we want to know, you look at the problem and you say, well, is this feasible? Is this doable? How hard is it? And so it's not always easy to know going in, but one good rule of thumb is where are you in the Whitehead tower of the orthogonal group? And so what I mean by this is a twisted blah structure. Well, what kinds of characteristic classes are you killing? So in unoriented Bordism, so there's no data at all, that is the easiest kind of Bordism. You killed no characteristic classes. So no information. And so you've made fewer choices, and so the Bordism problem ends up being easy. In fact, it's completely trivial. René Thom proved a long time ago, essentially that it's determined by mod 2 homology. You might think of it as the Atiyah-Hertzberg spectral sequence instantly collapses, however you like to think about it. And I mean, I think this is great. It's a very cool paper to read. So now let's say, well, why don't I ask for a little more? Why don't I say, I'd like the first Stiefel-Whitney class of my manifold to go away. So this is not a terribly, this is not a super demanding demand. And so this thing was studied by Brown-Peterson, and then the key fact was, the key work was done by Wall in 1960. And the theorem is that it's mostly determined by integral homology. There's a couple headaches, but they're not so bad usually. And you can sort of, especially in physically relevant dimensions, you can plan for them and work around them. But, so it's a little harder. Now, I want a spin structure, or something like it, a twisted spin structure, a spin C structure, a pin minus structure, things of that form. I have some kind of field theory, and it's got fermions. Now I'm in this regime. And now things are more of a headache. Wall wrote in the beginning of his paper, if one thinks that my results are complicated, they should try working it out for the spin group. And Anderson, Brown, Peterson did, not that long after. And they produced a complete description. If you're trying to take spin Bordism of something, it can start to get a little bit feisty. But ultimately, it's more difficult than oriented, but still, you should still try it. It's still likely to work. Now, let us ask for one more thing. Thank you. Now let's ask for a string structure, or a twisted string structure. The string Bordism groups are not known. If you figure them out in dimensions higher than 49, that's a new result. If you figure them out in all dimensions, that's something that homotopy theorists would be very impressed with. Depending on exactly how you go about it, you might resolve like a particularly feisty open question that people have been interested in for a while. But here, Giambalvo, Hovey and Ravenel, Mahowald and Gorbunov have made some good strides. Now, here we care about dimensions up to 11. So this doesn't really come into play. But even in the physically relevant dimensions, this is still harder than spin Bordism. You get more structure, which is good, but typically this is just the computation's worse. So we, in the example of E8 times E8 heterotic string theory, we're looking at a twisted string structure. So we should be worried, right? But it turns out that you can make this problem go away. and reduced to a twisted spin Bordism. Well, just a twisted spin Bordism computation. So the gist is an E8 bundle in dimensions, I think it's 15 and below, certainly in dimensions 12 and below, is equivalent data to its characteristic class C. So you can say, well, I want just two characteristic classes, P and Q, such that lambda of M minus P minus Q equals 0. So then once I know P, Q is uniquely determined, so the Green-Schwarz condition goes away, you have a twisted spin structure, and now that's much more easy to calculate. And so,
Heterotic string. What if you think the gauge group is actually E8 cross E8 semi-direct Z2, where the Z2 permutes the two factors?
I have really good news for what's going to happen in a couple slides. But yes, you're exactly right. The argument I gave is not symmetric in the E8s. And in its own way, that you could think of that as a big headache or as a fun problem to work on. So yeah, I'll say something more about that in a moment. But yeah, if you're okay breaking that symmetry, you have an easier computation, and what you learn, and this is something where I think Strong worked with the Atiyah-Hertzberg spectral sequence. It's that might be a nice example to try out. Though warning, I haven't personally done it, so I don't know. I learned this a different method. So the Bordism group vanishes though, and what that means, no anomaly, without having to think about anything other than what was the structure that we needed. So that's a nice theorem. What I wanted to mention is, well, what if the Bordism group is non-zero? Then you have to work a little harder. And it might still be that the anomaly vanishes. So how would you do that? You figure out what the Bordism group is, you figure out a set of manifolds that generate it, and then you just calculate the anomaly on each generator. And hopefully the generating set is small. Now, usually it is. So here's some examples where there's plenty of examples of people doing this. I wanted to highlight some examples. So Dan Fried and Mike Hopkins looked at the Z2 parity symmetry in M theory, and their generating set had 6 manifolds. And then in joint work with Matthew Yu, we looked at U-duality in 4 dimensions, although not the most general case. And then the other 2 papers are what I'm about to talk about next, which is about heterotic string theory with the Z2 action. So E8 times E8 semi-direct Z2 as the gauge group. So, okay, we've got this symmetry. Is it anomalous? And because, so you might say, well, why on earth should I care about it? But there is this thing in 9 dimensions called the CHL string, which is a compactification of the E8 times E8 heterotic string, where essentially on a circle with the non-trivial Z2 bundle, switching those 2 E8s. So if this Z2 symmetry is anomalous, that is a problem for the CHL string. So, if you're interested in the CHL string, you should go check that this anomaly is actually 0 so that this thing is well-defined. To be clear, enough consistency checks have been performed that no one seriously thought this is going to be a problem. So that's fine. So we're going to do a lot of work and get 0 out in the end. It happens. It's worth doing these consistency checks. And then as mentioned, Witten's argument breaks the Z2 symmetry, so you have to work harder. So, this is actually, this is a problem that I investigated joint with Ivano Basile, Matilda Delgado, and Miguel Montero. And so what we discovered, we did not calculate the Bordism group. We mostly calculated it. It's one of these 4 abelian groups of order 64, and it's generated by these 2 things. So one of them is the Bott manifold times RP3. What is a Bott manifold? If it is it's an 8-dimensional spin manifold, which is there's different definitions, but you can think of it as it has let's see. I'm gonna get this wrong, so maybe the right way to say it is, if you think of the index of a spin manifold as an element of K-theory, then this thing lands in K08. And in K08, there's a class called the Bott periodicity class, which implements the fact that K-theory is aperiodic, and the index of the Bott manifold is that class. So that's how you know a Bott manifold is a Bott manifold. That doesn't uniquely characterize it, but we didn't need to know which one we had. So the first one is bot times RP3, and the second one is you take a certain S4 times S4 bundle over RP3. So, okay, if this group is actually Z mod 64, then this is redundant, but that's okay. And then, well, we figured out what the anomaly is on these two generators, and we discovered, wow, it's 0. So the CHL string is okay. And I do want to mention, there's this really cool work of Yuji Tachikawa and Mayuko Yamashita, who provide a different argument that this anomaly and a lot of other anomalies should vanish. And if you have your physics hat on, what they're doing, it makes sense that it's equivalent to what we're doing. But even though they don't touch, like they're not checking on Bordism groups, they didn't calculate this Bordism group, they're doing something different with TMF. But it is not a mathematical theorem that these two approaches are the same. So it was good, it's good to have a consistency check. So how do we calculate the Bordism group? And the answer is, well, I mentioned, it's homotopy theory. So Pontryagin and Tom proved this theorem that says, well, in separate papers, to be clear, that says if you want to calculate Bordism groups, rather than drawing pictures, you could simply compute homotopy groups. Much easier. Well, in higher dimensions. And so the thing that you're computing the homotopy groups of, it's called a Tom spectrum. And so what are we going to do? So I'm going to be a little bit vague about the details here, just because of time reasons. But if you want to know more details, please come talk to me. I love talking about this stuff, and I'd be happy to work some examples with you, because I think it's a lot of fun. It's why I got involved in all this stuff. So the gist of it is, let's really do this from the algebraic topology perspective, which is the idea that if I extract algebraic invariance out of topological spaces, well, if you really just sit there and try and wring as much algebraic structure as you can out of this thing, there's a lot. So for example, cohomology groups are acted on by the Steenrod algebra of all the possible operations you could do universally on cohomology. That's a big algebra. That gives us a lot of structure. And if you think about it, well, these invariants are telling you something about the space. So topological information is constraining the algebraic information. So we turn it around. If you know that that's constrained, maybe you can say, well, I computed the algebraic information. It satisfies those constraints, therefore I learned something about topology. Now, working by hand like that is very hard, and not so many people do it. And it's much better to try and do this systematically, to build machines and then use machines which organize that information. So a lot of constructions in algebraic topology, they look scary, but they're not it's not that they're hard, it's more that there's just a lot of pieces. And so, you have your machine, you turn the crank, you watch that the gears flow, and then sure enough, you get your answer. And you go back and look, and sure, you have to, maybe you have to check some lemmas, but it's not as bad as it looks. And so, as you may have guessed, that's how I'm trying to motivate that spectral sequences are a reasonable thing. Unfortunately, even in the math community, spectral sequences are a little bit intimidating. So here's what Ravi Vakil has to say about them. If you have not read Ravi Vakil's algebraic geometry notes, or at least taken a look, they're really wonderful. His voice really shines through in things like this and many others. And he has a good introduction to spectral sequences with all the details. So what's the story? The story is you begin with an approximation of the right answer, called the E2 page. And if you're wondering what happened to the E1 page, that's usually used in setting up the spectral sequence. So you sort of, you begin at the beginning, not with the preface or introduction. And there are successive pages that you have to calculate, which make the approximation closer and closer to the correct answer. So when I say until you get the correct answer, there's one nuance called an extension problem that I'm not going to get into right now. But the point is, if you've gotten all the way to the end, you're pretty close. And again, there's a lot of moving parts. But the point is, those moving parts obey rules in the form of lemmas and theorems that say, this is what you should expect to happen, or this is what does happen. And so all that extra structure helps, it helps constrain. It means you only need a little bit of information. Apply that structure to it, and you've got a lot of information that helps solve the problem. So in this computation that my collaborators and I did, we used something called the atom spectral sequence. And I'm not going to say too much more about where it comes from. I just wanted to give you a picture. So this is the E2 page. Sorry. So the x-axis corresponds to the dimension in Bordism. So we're interested in this column labeled 11. The y-axis is something called the Adams filtration that is not so relevant directly right now. If you have 2 points connected by a vertical line, well, each point represents a z mod 2, and the vertical line says they're related, as in, for example, a z mod 4, a z mod 8. But the converse is not true. So in dimension 11, we see we have 3 dots here, that's a z8, 3 dots here, that's a z8. There may be a way that they're mixed too, right? They might be z8 plus z8, z16 plus z4, z32 plus z2, or z64. The other lines are extra structure. The slope 1 is saying taking the product with the non-bounding circle. This one is taking the product with S3 with 1 unit of H flux. And there's other structure not depicted. So for example, you see how this orange triangle and this orange triangle look exactly the same? It turns out that you can say algebraically, like there's some piece of the spectral sequence, like some element, which taking the product with it sends P1 all the way up to this class and takes this whole triangle and moves it up here. And that algebraic structure, you're looking at it, you're like, wow, there's too much information. Well, there's a general theorem that says that is the class of the Bott manifold. So if you know that P3 is RP3, which, this is in like geometric dimensions, so that's something you can figure out without having to worry about homotopy theory, then you know that this thing up here is the Bott manifold times RP3. So that's how we did that. Getting the class D required a little more work, but I can talk about more about that offline if you're interested. But the point is, see that there's a lot of structure here, and that structure gives you the information you need. Oh, okay. So the differentials, the grays are the differentials. They're going up, and so dr goes over 1 up r. So in the atom spectral sequence, this is not the same grading that people use in a T or Hertzebruch. Like really strictly speaking, it should be S and T, and then the differentials would be the same as a T or Hertzebruch or Sayre. But you can see how it's T minus S and S. And so that's why the differentials have this kind of funky looking form. And it has the advantage that vertical lines are the things you're trying to compute. Yeah. So the solid differential I know is non-zero. The dash differentials we left open, later I checked, I think they are 0. So you don't even have to worry about them. So just to summarize, we did this computation, we figured out what the Bordism groups were, and then in dimension 11, that's really the one that we're interested in. It turned out that the 2 generators, the anomaly vanishes on them. So rather than having to check on all 11 manifolds with the right structure, we just checked on 2, and we discovered they're 0. Or the anomaly is 0. So I've got just a couple minutes, so I'm going to talk about the one case where the anomaly does not vanish, and then I'm going to say a little bit about some things that might be fun to think about in the future. So it's not necessarily terrible that anomalies vanish, but if you have 2 dual theories, dual in the sense of physics meaning isomorphic, then they better have the same anomaly. So if you checked one side of the duality and you discover the anomaly is 0, and you check the other side of the anomaly, or the other side of the duality and you discover the anomaly is non-zero, you have a problem. And there's lots of string dualities. That's lots of places for things to possibly go wrong. So in particular, type 2B string theory with this duality symmetry, lots of consistency checks performed on that, the anomaly better vanish. So as you can tell by the red text, maybe something funny is going to happen. So I'm going to go over this a little bit fast due to time, but the tangential structure it's a twisted spin structure. I'm looking for the structure group to go from GL and R to spin times the metaplectic group mod plus minus 1. But if you include the world sheet orientation reversal, you can actually extend to the pin plus cover of GL2. So these are twisted spin structures. So this computation is easier than the one I discussed before. This paper of Agnes Baudry and Jonathan Campbell, you should check it out. It's a really good introduction to these kinds of things. And really it comes down to how bad is GL2Z's classifying space? How bad algebro-topologically is it? The answer is it's pretty great. You can replace it with the dihedral group, and now you're doing great. Like, things are pretty straightforward. So here's the spectral sequence. It's again an atom spectral sequence. So we're interested in dimension 11. And this is the E2 page. And this looks bad. There's so much stuff here. But there's a lot of differentials. So when you're done at E infinity, you just have this thing. There's 4 copies of Z2 here, and then these 3 are going to combine to a Z8. which I can say more about offline if anyone wants to know more about it. So we calculated the Bordism group. So this is me, Marcus Dieriegel, Jonathan Heckman. I'm sorry I left an M out of his name. So sorry for the confusion. And then Miguel Montero. So we got the Bordism group. There's some 3 primary torsion that I didn't show in the spectral sequence that we found using a different spectral sequence. But look at this group. It's big. It's generated by these manifolds. These are some names for some manifolds. And okay, you have to figure out what the anomaly is. There's an eta invariant associated to fermions. And the self-dual field's contribution is a little more interesting, worked out by Xie, Tachikawa, and Yonakura. And it's something to do with an ARF invariant and a quadratic refinement of the torsion linking pairing. And so what we discovered is something truly concerning, that the anomaly is not 0. Like, this is not good. This S-duality really ought to exist. Like, this theory should not be anomalous. This is like kind of concerning. String theory ought to be there, right? And so this is not the end. One thing you could do is you could insert a correction term into the 2B action that makes this problem go away. And this seems parsimonious because there is a term that works, and it only works, like you can only do this for the specific anomaly that we found. And so this is one of these like string theory coincidences that keeps lining up. So that suggests that this is really something canonical. Another thing that you might say is, wait, shouldn't the type 2B RR fields be quantized in K theory and not cohomology? Yeah, but like it seems this is not something that we were going to resolve in this paper. Reconciling S-duality and K theory, like no one knows how to do it as far as I know. It's an open problem. And so we don't like that. So maybe the sign is, well, we should have been using K theory, but I don't know how to reconcile those. So at least for the part of GL2+ that we know how acts on K theory, which is a pretty small part, it'd be really interesting to say, actually, let's run this calculation for K theory and see if it makes the problem go away. So in the last minute, I'm going to mention actually just one thing that is some work in progress with Matthew Yu that I think is interesting. So Sanath Developurkar has defined something called a string H structure. And this is the string version of a spin C structure. There's also, so when I say that, there's different things you might mean. So if you're thinking about something called a string C structure, this is different, and it generalizes in a different way. So what we've learned is that this thing looks an awful lot like the data needed for type 2A, and in particular, a string H structure gives you the condition big W7, the integral Stiefel-Whitney class, vanishes, which is the condition that Diaconescu, Moore, and Witten discovered when studying type 2A, in their paper. So this is an interesting suggestion that somehow in type 2A string theory, some sort of string H structure or twisted string H structure is behind anomaly cancellation. Moreover, another calculation that Developurkar made, it's a purely homotopical computation, and its consequence is that string H Bordism is easier to calculate, usually, than string Bordism. So what we're in the progress of doing is figuring out exactly the relationship between 2A backgrounds and what's needed for 2A string theory and string H structures, and hopefully using that to produce some easier than the string computations of anomalies. So I am out of both time and slides. So thanks so much for your attention. Thanks so much for your questions. And yeah, does anyone have any more questions?
Is there a guess for what kind of structure to think of in M theory?
So I mentioned a while back there's this, let's see. So there was this paper of Fried Hopkins that I mentioned. Yeah, Fried Hopkins, it's called like Consistency of M theory on unoriented manifolds or something like that. I don't remember the exact title. And so they answer the question of what is the structure. Well, okay, let me be careful. I don't know if they were the first people to say what is the structure in M theory, but they calculated the Bordism group for it. And so that structure is known. It's a pin plus structure and a lift of the fourth Stiefel-Whitney class to twisted cohomology for the orientation bundle. So, so maybe if you add extra structure into M theory like branes or something, then you get some, then there's more open questions there. I'm not really sure, but certainly as it's, with just that stuff, it is known.
I see, yes, because what I'm curious about is like if I add the G4 flux or something like that.
Oh yeah.
So then you have this kind of nonabelian twisted condition come from the G4 flux, right? It's kind of hard to think of how what kind of structure you should think of, I guess.
So, okay, so what I know is that Fried-Hopkins did consider the G4 flux. That's their integer lift of W4. The word non-abelian makes me worried that I am not talking about the thing you're talking about. I'm not sure. At the very least, let's talk about this some more sometime this week. But so either their answer, their formalism is a direct answer to your question, or if that's not true, then I think what you've done, like what you're asking about has not been done yet. That's what I think.
Thanks.
So going back to the SL2Z anomaly in 2B.
Yes.
So where in that calculation did you use that Ramond fluxes should be classified by singular homology?
So let's see, where is the, where did I mention? Let's see.
Yeah, there.
Yeah.
So where is that making a particular choice of generalized cohomology theory for the Ramond sector?
So one answer to this is that at the very beginning, the fact that we have, okay, so here's maybe a concrete answer, which is one of the terms in the anomaly is is associated to the self-dual field.
Right.
And
so it's the way you handled the self-dual phi form.
Yeah, like the fact that we have the torsion theory and cohomology,
Okay.
not K theory.
So maybe we should so you found the anomaly is not zero.
Yeah.
So S duality is wrong.
Well.
Wait, let me finish.
Okay.
Well, there's a meta theorem that S duality holds. So isn't the conclusion that that's the wrong generalized cohomology theory for the Ramond sector?
I think that's a fair conclusion. But then, how do we reconcile it with SL2Z? Yeah. Well, that's why I think this K-theory computation would be cool. Because if the small amount that we do know how to do makes the problem go away, that's a really strong sign that that's the direction we should be going in. Oh no, it's something, I think it would be fun to do, but I haven't worked on it.
There's some elements, of course, of the SL2Z group that are not going to take you from weak to strong coupling. So it better vanish for those. Yeah.
Yeah. So I think that would be a good thing to do.
I think there was a section that you passed over on orbifold anomalies.
Yes.
Is there like a canonical kind of answer to what these are supposed to be?
So, I mean in the sense of what's the mathematical formalism behind them or what kind of Bordism should go in?
Yeah, that.
So part of the question is well, things to study. What's the answer to that question? But people have definitely, so I learned about this thing. I didn't come up with this idea myself. I learned it from Miguel Montero, who had talked to a couple other people about it. The question is, okay, if we're looking at orbifolds, which are sort of locally, they're like manifolds with a group action, then maybe what we want is Bordism of manifolds with a group action, or Bordism of orbifolds, something like that. And if you tell this question to homotopy theorists, they will say, yeah, we have some answers on that. You can set the theory up, but the computations are quite hard. And so this bolded question of well, what is the classification of invertible field theories on orbifolds? That would be that's a pure math question whose answer would be sort of the key to unlock this proof strategy for anomalies on orbifolds. Okay. Was that the kind of answer you were looking for?
Yeah.
Okay. You. Cool.
Sorry, I didn't quite get something toward the end. I think you mentioned that to fix this issue of SL2D in type 2B, you also had the possibility to add a term in the type 2B action, is that right?
Is what?
Is it right that you can add a term in the type 2B action to fix it?
So that's what we did, and to make it go away.
Yeah, but this is quite confusing for me, because typically you cannot cancel anomalies or modify anomalies by just adding term to the action. Anomalies are supposed to be robust under deformations. So either you do something very drastic or you have to add fields. So why is this working?
So when you say because adding terms to an action, you can like scale it down to 0 and it has to go away?
Well,
maybe, okay, I'm not sure if this is an answer to your question, but the term we added is torsion. And so that means it's hard, like, that, you know, the discreteness of that, it might be the robustness that you're looking for.
Oh, okay, I see. It's not something with a tunable parameter.
No,
okay,
no, it's just, it's that and you can't do anything with
it. So it's a very drastic modification of, okay, thank you.
I want to, you mentioned that cobordism and bordism are basically the same thing. Can you please elaborate?
Okay, so bordism and cobordism. So, you know, when people first started thinking about this, they said cobordism, as in this and this, jointly bound, they co-bound this thing. So cobordism. Then Atiyah wrote this paper called Bordism and Cobordism, where he pointed out